Good afternoon, everybody. My name is Edward Miller. I'm a research product manager at Meta Reality Labs Research, and it is my pleasure to introduce the inaugural EgoMotion workshop at CVPR. We've got a really exciting lineup from a huge array of speakers to talk about their work, about how we can better predict the position of the human body from egocentric sensors and devices. Without further ado, it's my pleasure to introduce Richard Newcombe, Director of Research Science for our group within Meta Reality Labs Research. Richard, over to you.
Thanks, Ed. I think I can turn this off right here. Is that right? Or, all right, I'll leave it on. Okay, thanks for inviting me over for introing this. I'm going to actually give a really broad introduction that hopefully connects a few dots across over the space where EgoMotion is really vital. And notwithstanding that there's a lot more even than what I'm going to show, hopefully you'll get to see some demos that sort of like broaden this out. But I'm going to come from it from a point of view of EgoMotion, as in really getting to a full body model, a predictive model of a user who in this case is starting to wear something like a pair of Ray-Ban from Meta. And future devices like this, these wearables, are sort of extremely exciting for researchers who are in this EgoMotion space. If for no other reason than you start to really get data from the wild as to what it is that they're looking at. In the case of Project Harry that I'll go through, it has eye tracking, it has a microphone array. But these are products already that are in the wild that allow us to sort of get data in distributions that are much more realistic than has been observed in the lab in the past. So hopefully, and within just 13 minutes from now, when I shall be taken off stage, I will have given us a broad overview of how EgoMotion relates to really getting to what we call contextualized AI. That really helps us solve for a lot of problems, with headsets and various other applications. I'll then take us into how Project Aria in particular is helping us get new kinds of data for EgoMotion estimation. And EgoMotion in the more broad sense of sort of everything that a human state might be, not just the underlying kinematic and dynamic exterior pose. And I'm also going to close the gap on the fact that there's a lot more context to be had from the devices that are going to allow us to obtain EgoMotion. And we both need these models of external reality, the environment model, if you like, as well as the human model. And we need to estimate these things jointly together. And I'm pretty sure we're going to see a fair bit of that from the speakers today as we start to sort of engage with the fact that actually estimating EgoMotion is really not a human body only thing. Okay, so back to the big picture. It's funny, I've been giving this talk in various different forms through the first 2 days of the conference. I'm sure there's more to go. It's hard to believe that between sort of Turing, who certainly was hypothesizing about AI in the 1940s, and where we are today, that essentially a lot of the problems would end up being solved, and we'd be actually sitting here in 2024 with the advent of wearable devices that can actually deliver forms of AI from an egocentric perspective. But it did happen, and certainly I think we're getting closer to the vision that Turing and his pioneering colleagues had at the time of what computing would become. That is to say, with robotics, with engagement in natural environments, rather than in the kind of forms of 2D screen interactions on mobile phones as computing has become so far. So that's important, that we're actually coming full circle back to AI as was really being envisaged in the 40s and before that, embodied AI essentially. And the other great thing about EgoMotion that's worth connecting for the folks who are doing it, you're doing it for a reason. Usually EgoMotion is something in the course of solving an application space. And another great sort of thinker, Kenneth Craig, who was a psychologist and general philosopher in the space of models of minds, had a very simple point to make, which is still true today, which is that from a point of view of humans and how we understand and interact with reality, we as an organism carry around a small scale, if not a complete model of external reality, and we understand how our actions can impinge on basically that environmental model. So if we have a model of how we can interact with reality, then we can try out various different alternatives to our actions. We can conclude which is the best of them. We can react in future situations before they arise. And we can utilize the knowledge of past events by remembering them within that model so that we can react in a much safer, fuller, and more competent manner to the emergencies that face it. Well, that's from an evolutionary perspective, why, for example, humans utilize their EgoMotion with a model of their environment so that they can essentially forward predict what might happen next. But at the heart of most of our applications, whether it's driverless cars or decent motion models that are in VR today, actually there's that same concept of a predictive model. And in this case, like the human body model is at the absolute center of what causes change in reality, whether it's in VR, XR, or in fact the future of contextual AI. Okay, so the other news, in case you didn't get it, is that AI is here. So good on you for working in EgoMotion and rather than in large language models from internet scale text, because clearly that got solved already. At least this kind of AI got solved, the sort where you interact with it using text prompts and sort of like tell it a little bit about what you want to do, and it might answer you in sort of like sophisticated ways, but certainly it is missing something. Because it's built on internet scale textual data sets, then actually it's missing the main thing, which is essentially your real life context. And it's at the heart of your real life context where we're going to find your EgoMotion being the main actor that we need to be able to capture and not just store, but continuously represent in a way that allows AI to understand what you're doing in reality. So this is where we go full circle with AI and wearables, where actually for the first time, things like Meta Ray-Ban glasses allow you to capture, from where you are in your actual physical environment, other kinds of modalities that will allow us to understand what's going on. There's other sorts of devices that are going on there that aren't about EgoMotion, but they're certainly important when you extend EgoMotion into the space of like what is the state of a human, of which EgoMotion is a significant part. Observing your egocentric reality is what really is missing from AI today. Okay, so great. Devices exist. Hopefully some people have got these devices. Actually, who has got a pair of Ray-Ban Meta? Has anyone got one? Wow, that's a lot more than I thought was going to be. That's great. So hopefully you're getting to use the features like, hey Meta, look and see. And today, that is a form of contextualized AI, but it requires essentially you to trigger what's going on. Whereas what we really want is what we'll call always on contextual AI. Well, let's start with contextual AI. That's taking your context, your physical plus digital perspective on reality, a timeline of it, if you like, with the events that are happening as you move through and interact with reality. Put it together with that good old-fashioned or modern version of AI, and what you have is contextual AI. Now, when it's always on, so that as you continuously move through the day, then what you have is a very different type of AI, one that's constantly observing your reality and can start to make inferences from very subtle changes in your EgoMotion to very big patterns in life. So think about what it's going to take for us to get from me triggering a Ray-Ban Meta today, where I have to say to it, hey, what's this, to it being able to tell me, effectively interrupt in a way that's useful to me when it knows that I want that information. Now, for that to be the case, the sensing needs to be always on, and the computation for the estimation algorithms need to be always on. And more importantly, we need to move from internet scale data sets to data sets that are around this kind of egocentric space. And that's where Project Aria comes in. So Project Aria has been developed since about 2021 in public, where you can go to projectaria.com and you'll find there some very nice data sets that look a little bit like this. These are sort of what we call egocentric, so they're outward-facing cameras, but there's also inward-facing, so eye tracking, microphone array, 7 microphones, 2 IMUs to be able to capture high dynamic range of the wearer, and a host of algorithms that we provide through what are called the machine perception services to be able to process that into useful data, including the head pose, the hand pose, the eye pose, and various other sort of good stuff. We've got lots of partners, and we'd love to have more of you as partners of this program as we start to investigate and understand like where the real value is of egocentric data in research. Okay, back to predictive models of reality. The problem that we've got is that in essence, the kind of data that we are producing from Aria is too big to store. It's too big to compute with. We're talking about petabytes of data per person per year. So instead, what we're going to talk about is a 3D model of reality that can be created, interact with the human or agent model, which is where EgoMotion is going to come in, and then understand that interaction through a model of the human or agent and the world. These things can connect together in really obvious ways from a point of view of decomposing the problem into things like your EgoMotion, which can be obtained quite well, as we're going to see soon, from glasses, together with the fact that it's not about the motion of the body in isolation, it's how it's changing the environment. And so we need that model of the world. And then we need to provide both of those things to the future AI. In the case of the 3D world model, we've been working on this in our teams at Meta. We call it live maps. And essentially it comprises a stack of spatial AI technologies that allow us to get context to AI about what's going on in a user who is a glasses wearing user. So we obtain external maps that then a user with a pair of glasses or a VR or XR headset can localize back into to give them context about where they are. We need to estimate the surfaces of the things around the user and give them labels, the structures, the floors, the walls, the doors, the windows, and so on. We also need to be able to get the objects in the environment that the user is interacting with. We then put that together with a human agent model, a full 3D human agent model of the body moving around in space dynamically. But beyond that, we also start to extract the events of how the human is interacting with the environment. So if we move beyond the EgoMotion and say, well, what is it the person is looking at? Well, that is kind of EgoMotion. Well, what about what they're saying? Well, that's certainly part of an ego human. Where they are, what they're interacting with, what they say, etc. This is the full event space of a human. And we want to be able to capture all of that because that is the context that is useful for conditioning future systems that need to know what the user is trying to do. We put those things back together. What we'd really like to do is be able to have EgoMotion and effective event estimation through an entire day of the user, from when they wake up to when they go back to sleep again. And the challenge here is that calling a thing an event is in itself sort of like ambiguous. What I may call walking my dog, you may call sort of something very different if you see the sort of games that we get up to in the field. The point is that the granularity with which we need to capture motion of the user interacting in the environment can change as a function of the length of the context window and the actual task or challenge that they're trying to solve. So what we're interested in here, I'm going to actually just pass a little bit faster through this, is capturing a sufficient model of the user and their reality and how it interacts. And in general, that's what Project Aria is there to do, is to accelerate all of those research tracks to get us there. Can we just give the fine-grained ego data from Aria to an LLM and solve all of our EgoMotion and various other problems? Actually, the answer is going to be no, although I really think people should continue to research this space because it worked very well for text. The problem in general is the size of the data sets. They simply can't exist in the A100s, at any kind of scale, internet scale in particular, to do anything useful. So that's why we're working on these kind of encoders, like, for example, full-body EgoMotion. Let's skim over the challenges with the data. So this is where we get to building this model. Kenneth already told us that if we build a model of reality and keep it up to date, it's going to be useful. We've looked at the spatial AI components for the environment, and what we need instead is to also look at the body model, the human, and how they interact with the environment. How are we getting that human? Well, luckily, that's the rest of this workshop. So what I can tell you is this: if you stick around for the rest of the day, you will find out how it is that the teams at Meta are obtaining that virtual human, which is in fact one of our lead researchers, in their apartment as they walk around their space in nothing more than a Project Aria device and interact with their environment and keep that model of reality up to date. Now, there's a lot more to EgoMotion from a point of view of applications than contextual AI, but I do think it's the particular space that bridges a lot of the problems that need to be solved in a more unified way. With that, I'm going to hand back to Ed.
Thank you very much, Richard. And please do stick around in the break. I mentioned to chat with the professors and speakers here, but also to try out those demos. And it's my pleasure now to introduce Siyu Tang, Assistant Professor from ETH Zurich. Please welcome Siyu.
Good. Thank you very much for the introduction and for the invitation. I'm very happy to be here to present our works on egocentric 3D human body estimation and synthesis. So just a bit of introduction. So we are talking about the age of autonomy, right? People start to build autonomous cars, like not start, but really building autonomous cars, autonomous robots, and also embodied devices. And if we want all these autonomous agents to work together with humans to assist humans performing different tasks, they need to see and understand the 3D world as well as the human in the 3D world, right? So that's a motivation why in my group we really work on human motion and human behavior understanding. And in this talk, I will be focusing on egocentric human motion understanding. So basically reconstructing 3D humans in 3D scenes from egocentric views, as well as egocentric perception-driven human motion synthesis. The first work we have been doing in this direction is like ego body, a data set. So the reason we capture this data set is because at that time, we are very interested in human social interaction, like human-human social interaction. And if you really want to understand human social interactions, I would argue like this egocentric view is actually a very good modality, right? It's really captured from the view of the interacting people, right? You really see the facial expressions, the body pose. So, but at that time, there were not really data set in this direction. That's why we captured this data set, ego body, human shape and motion of interacting people from head-mounted devices. So how we capture this data? So basically, we basically have two people, normally have two people interacting with each other in a 3D in a room. And then we have 3 to 5 Kinect cameras to capture the body pose of this human to reconstruct the pseudo ground truth. And then we also have 1 people wear HoloLens. And then we synchronize the Kinect and HoloLens. And then what we have now is basically the 3D motion and body ground truth from this egocentric point of view. And besides this 3D human motion ground truth, pseudo ground truth, we also have the 3D scan of the environment as well as the gaze and hand tracking, head tracking of the camera wear. So basically, based on this data set, now we can try to build models to understand human social behaviors from egocentric view. So overall, we captured 125 sequences, 15 indoor scenes, and about 200K frames, right? So that was 3 years ago. I think compared to the data set these days, it's a small scale, but it was enough to keep 1 PhD student busy for 1 year. So that's how we did that. And after we have this data set, right? So our ultimate goal is to understand social interactions, right? But the first thing we want to do is basically to estimate body pose, body gestures from this egocentric point of view. So that's basically the second work we did in this direction, ego HMR, probabilistic human mesh recovery in 3D scenes from egocentric views. So again, right, the task is given this egocentric image, we want to estimate 3D body pose. And this is actually a very challenging task because from this egocentric view, you have lots of motion blurs. And when people have like social interacting with each other, they are close to each other. So you have lots of truncations and also human interact with 3D environment. So you also have body environment interactions. For example, sitting on a chair, you don't really see the lower body part. So it's very hard. And the idea we had at that time is, okay, let's try to make some assumptions. So one assumption we made is, let's assume from these egocentric devices, we also have a rough understanding of a 3D environment, like a 3D scene point cloud, something like that. And given this rough understanding of the 3D environment, as well as the egocentric view, now we know which pose as estimated from this image is correct, right? Because we know the 3D environment and we know this is the right pose. So this means we want to design a model. So we want the model to have 2 properties. So the first property is it is a probabilistic model because we really have partial observations, right? So we don't want a deterministic solution. We want to model a distribution of potential body poses. So it has to be a probabilistic model. And the second thing is this model should take scene and image observation into account. So it should have ability to perform some conditional inference, right? So based on these 2 requirements, we basically leverage the diffusion model, because diffusion model actually you can train classifier-free conditioning, and you can also have some loss guidance later to help you to refine the result during the diffusion process, right? So that's why we use the diffusion model. Just a little bit in detail. So the diffusion conditions basically have the scene, like a 3D scene encoding, so some point cloud around the human, and we also have images. So we have an image encoder, and we also run open pose. So this open pose tells us roughly which body part are visible, which body part are not visible. And this conditional information goes to the diffusion denoiser. And for the denoiser, we actually leverage like a graph convolutional neural network based on the body kinematics. And the reason we did that is because by doing this, now we can really make the conditioning, make the body part conditioned on, like different body part have a conditional information, right? So we can say, okay, this body part is probably not visible, this body part is probably visible, and then by having this information, inject this information into the model, we can get a better prediction. Besides this, classifier free-based conditioning, we also have a collision guided losses during the diffusion process, where we have the the occupancy of the human body, and then we can compute a differentiable, we can compute the gradient with respect to the body parameters, such that the body is pushed out from the environment, right? Like basically we can reduce the human-scene interaction during the diffusion process. So what we can achieve with Ego HMR is, first, we have relatively accurate pose for visible body part, and here are examples. And we also have plausible human-scene interactions, even though we don't really observe the body, because we take really scene into account, right? And we can also perform like a diverse sampling. So basically, given input image like here and the 3D scene, and then for the visible body part, we have an accurate estimation, and for the occluded part, we can sample different plausible body poses. And I think this is really important for the next project, because now it's just a single poses, right? Ultimately what we want is full motion, right? The motion of this person who appear in this egocentric view. And this is a very challenging task, because you also have this very a dynamic egocentric movement, and this person might move out, might be occluded. So for the full frame model, it's important you really learn a distribution of plausible motion, and later it's better, then it can be used for temporal modeling. So that's all for the first part. And in the remaining time, talk about egocentric perception-driven human motion synthesis. I will slow down a bit then. Very good. So my group started to study human motion modeling, a synthesis virtual humans, since 3 years ago, right? And then when I present this motion synthesis models to computer vision groups, people sometimes ask me, why do you want to work on motion synthesis? Is it for computer games, or for character animations, or for some applications in metaverse? For us, the reason we really study not just this work, but we really study human motion models is because I want to bring realistic virtual humans into the real world simulator. If you take this autonomous driving application as an example, so autonomous cars, right? They often first trained in simulator, and in simulator, if we want these autonomous driving cars to behave really can really be used in the real world scenario, they need to see realistic human behaviors in the simulator, right? So that's why I think it's really important to study the models that can model the human behavior, and then can have a human behavior learn a distribution, and then later we can sample different human behaviors in the real world simulators, right? And if you have this application in mind, and then the question is what kind of model would be needed. I would argue, right, the first requirement should be generative. So if you want to bring virtual humans into simulators to train perception models, you really need to generative model where you can sample, right? And it should be efficient and also diverse. So real human, we have very diverse behaviors, and we need a generative model that can generate diverse samples, and then we can bring the samples into the real world simulators to train the perception models, right? And also controllable, because we might get some feedback, for example, for certain cars, right? For cars, certain human behaviors they cannot really detect, this type of pedestrians, and then we want to be able to control this generative model so that we generate more data for certain scenario. Okay, so that's the motivation. And so we have several works, like for the past 4 years, on human motion synthesis. And actually, this is the first work we show, like when the synthesis, the human motion, can be used for training better perception models. So this is EgoGen, an egocentric synthetic data generator, and it will be presented this year, CVPR at oral on Thursday. So what does EgoGen do? It's basically, it's a synthetic data generator. And if you think about when you want to generate synthetic data for egocentric perception task, what is really important is you have a realistic human behavior model, right? So human behavior needs to be realistic, and then the cameras that are put on the human head, right, embodied devices, and then you can capture like realistic, like embodied data, right? So for EgoGen, what we can do now is to basically, these are the data captured from the virtual humans that are synthesized by EgoGen. And you can see we can provide different type of ground truth data, for example, depths, data, normal maps, semantic segmentation, and as well as, for example, bounding box, detections, word coordinates, and also we can synthesize motion blur. So this is the overview of EgoGen. So it has different components. Of course, we need a render and an annotation component. And besides that, we also have a sensor placement. So for now, we only synthesize either the RGB or the depth cameras, like facing forward cameras on the human head. But of course, we can also try to synthesize, or there is a potential to synthesize other type of cameras, for example, IMU cameras, or the cameras on hand or cameras on foot. So I think there is a potential there. And the second component is automatic closing simulation. So we need multiple people. We cannot just synthesize one people, right? We need lots of people in the 3D environment. And in order to make this synthesized image realistic, we also need closing like textures and closing animations. And at the core of this EgoGen is actually this egocentric perception-driven motion synthesis. So there are different ways to really perceive the environment when you try to generate human motion in an environment. For example, you can try to encode SDF or other things. And I think to generate realistic egocentric behaviors, the virtual human's perception of the environment should be really egocentric. So that's what we did. So here we have like the virtual human observe the environment by their own perceptions, right? So that we have like a compact representation of the egocentric perception, and this representation is a representation of the world around the human, and then this drives the virtual human, and the virtual human moves, and then the egocentric perception change. So we basically close this loop of perception and action for this virtual human. So the key advantage, for example, we have egocentric perception driven, so it's more like an egocentric behavior. And another thing is there is no path planning compared to the previous work, and also there is some emergent multi-agent behavior. So you can check the website. We have never trained in the simulation where there are many people, but actually now when there are many people like this virtual humans, they can actually avoid each other. So it's quite nice to watch that. So egocentric sensing-driven motion modeling, the one key is how do you really model the environment, right? So here is, as I mentioned, we have this egocentric perception, but unfortunately, the whole thing is RL-based. We were not able to really take this whole image into the RL algorithm to produce some representation of the environment. So what we did is this compact egocentric sensing. So basically kind of shoot a ray from the eye and then two rows of vector, right, based on the human movement. So we call this compact egocentric sensing, and all this information goes to a MLP. So basically this part represents the state of the whole thing, right? So it has like the body representation. It has the environment representation based on this egocentric sensing. It also have other things, for example, how far I'm away from the distance and what's the remaining time in this here. And also, for example, we can put other state, for example, the gaze of the person, where the person is looking at. And all this information go to MLP, and we use a PPO algorithm to optimize the stochastic policy. So we run, we sample action from our policy network, and then this action basically drives the virtual humans to move forward. So, and then this motion changes the egocentric perception, basically change the state, and then we have the next action to further drive the virtual human. So we have this loop here. So as I mentioned before, like given this human motion synthesis model, genetic motion synthesis model, and given some 3D environment and some graphics assets, now what we can do is to populate 3D environment with virtual humans, and then given all these things are like graphics assets, now we can really have the ground truth for these egocentric views. For example, depths, optical flow, bounding boxes, semantic maps, semantic segmentations, and as well as normal maps, all kinds of ground truths. Next, I want to talk about application. So now we have this way to generate synthetic data, right? Can we really use this synthetic data for some perception tasks? So in the EgoGen paper, we show 2 applications. The first one is mapping and localization for AR. The second one is human mesh recovery from egocentric view. So for the first one, here is a task, right? For the mapping and localization, for example, for HoloLens, in this case, in our case, is you want to capture the data of a huge environment from these onboarded devices, and then what you want to do is to create a structure from motion map of this large environment. And later, this structure from motion map can be used to localize images, right? To localize AR devices weared by other humans, right? So this is AR localization. And the problem of current pipeline is it's hard to capture, right? You can ask some virtual humans to walk in the 3D environment, but it's just the data you capture is very sparse, which means the structure from motion map is also quite sparse. Right, and this influences the localization accuracy for the AR devices. And what we did is very simple. So we have the 3D laser scan of the environment, and what we did is basically we populate digital humans in this environment, and now we can generate lots of egocentric synthetic data. And combine this egocentric synthetic data, like put this egocentric synthetic data into the structure from motion map, now we can get a much complete and denser structure from motion map. And in the paper we show this actually helps this actually improves the localization performance. So the second task application we showed is egocentric mesh recovery. So again, the task is, as I showed before, right? You have an egocentric images. You want to estimate 3D human body from this egocentric image. And as I mentioned, right, it took my student 1 year to capture 125 sequence, right? So it's a very, very expensive way to, if you want to capture such data, it's very expensive. So now with EgoGen, what we can do is to generate synthetic data. So we leverage EgoGen to generate 300K RGB and 105K depth images for training for people moving in the 3D environment. And you can see these are some examples. And with this synthetic data, we basically actually can improve the performance of state-of-art method by 20%. So the thing is, we pre-train our model on the synthetic data and fine-tune a little bit on the real data. So we were not able to generate data that can be directly used. So we still need a bit of real data. But I think we are getting there, right? With a better and better graphics assets, people have already shown, right, like a 3D body estimation from synthetic data can be trained with, like, can be used in the real world scenario. The last thing I want to discuss is future work and potentials. So on one hand, I think we have this egocentric synthetic data. It's very first step. We only have people walking around, right? So if we have a better model for human-object interaction, for human motion, human-human interaction, we can increase the range or the capacity of this egocentric synthetic data, right, with better motion model. And essentially, this egocentric synthetic data, they provide accurate and rich ground truth annotations, right? It's accurate, it's ground truth. It's some, for example, the normal maps, the depths, you will never be able to annotate them, right, from the real data. On the other hand, we see really amazing data, for example, from Lingni and from EgoXO. So these are real-world data, and they are semantic rich and diverse, right? But they are lack of certain type of accurate ground truth annotation. And I believe these two types of data are complementary to each other. One is accurate and rich ground truth, one is semantic rich and diverse. And these two types of data, I think, can facilitate the learning of egocentric foundation models. Yeah, so I basically present 3 works, and these works were led by my students Ziwei and Jiang, and that's all from my side. Thank you very much.
My pleasure to welcome Christian Theobalt from Max Planck. Please welcome Christian.
Thank you so much for the kind introduction. So it's a great pleasure for me to present some of the work we do. So I'm a director of the Visual Computing and AI department at the Max Planck Institute for Informatics in Saarbrücken. And I'm also director of a new center we have at the MPI, which is called the Saarbrücken Research Center for Visual Computing, Interaction and AI, which is the result of a new partnership we have with MPI for Informatics and Google. And in the department, we are generally interested in research problems at the intersection of graphics, vision, and machine learning, building models of the real world and building models of humans in that real world. And all the aspects that basically contribute to this is an important direction of the work we do. And now in particular also working on using egocentric devices to capture the motion of humans is something which we work on. And in this presentation I'm going to show you some of the recent works we did together with my PhD students, and also most of these are actually presented also at the main conference here. So here's a little overview of the presentation. I will begin with a little motivation for why this is an interesting field of work, and then essentially basically have different techniques which use essentially slightly different versions of egocentric sensor setups. So we heard a lot about the motivation here already. So why is egocentric capture important? I think there are certain application areas, you know, extended reality, VR, AR. If I want to move around, I wear a device and I basically need for immersing myself into that virtual space, also the estimation of my pose. I would ideally like to have 2 things, right? I would like to have a setup that can do that with as little as possible instrumentation on me, and also which doesn't spatially constrain me, because otherwise I cannot walk around arbitrarily in space. So the question of how to do it with as little as possible instrumentation is something that, you know, our research community has looked into, but mostly for the outside-in view. Like markerless motion capture is something which, you know, we've as a community have worked on, also my team for some time. And this allows you to basically do pose estimation without body instrumentation, but you still have the issue that you're essentially constrained to the space where your camera stands in order to be captured. So ideally, what you would like to have is if with the sensors that I'm, you know, taking around with me, I can already capture this. But this is already still nowadays quite hard, right? It's still a struggle to actually do this with the sensors that are essentially attached to these devices that we have. And this is what we as a research community, also the people in this workshop, are looking into, right? So basically to develop methods that use the data from the egocentric devices. And for instance, this is what we most of the time look into, downward facing fisheye optics cameras, which you can attach like to a hat in this case, or basically simulating as it would be, so to say, part of a device. And from that try to estimate the pose. And these are 2 example earlier works from this field, one from us and also one from the colleagues from Meta. Now, of course, we are not the only ones looking into this, right? So there's a large community looking into this. And if we think about egocentric motion capture, you could classify this into different categories of works according to multiple dimensions. So here I'm classifying it according to mostly the setups used, right? So we have some methods that essentially, as the top left, use forward-facing cameras. So it's a camera that's egocentric, but it's not set up such that it looks at you, but the environment. It's also a fascinating problem, right? But that's not what the rest of this talk is going to be about. And then we have other works which use multiple sensors, in multimodal sensors, right? It could be other on-body, for instance, accelerometers plus cameras. We also did a bit of work on this, but mostly what I'm going to show is about the downward-facing egocentric cameras and how to estimate pose from there. Now, when you try to do this with such a setup, there are multiple challenges that arise. I mean, first, doing pose estimation from an image alone is, even in the non-egocentric setting, already a challenge. But some of these challenges maybe even, strengthen or become even more strong in the egocentric setting, right? So there are multiple challenges that we face there. One is essentially the lack of data sets, right? So we have learning-based approaches. How do you get good data sets to that provide ground truth, also to train these methods on these challenging camera poses? There's simply also the challenge of estimating global pose, right? I mean, with a device that I carry around with me, and I still want to know how I'm actually moving relative to the environment, still a challenge. Well, the positioning of the camera poses multiple additional challenges as well, right? I mean, ideally, it should be, ergonomically speaking, probably as close as possible to the head, maybe like in a headset, but from the algorithm perspective, it would, on the other hand, be much better if it was further out, but that's not, something that everyone is ever going to wear. So there is, so to say, some form factor limitations. But then in addition to this, in order to be able to see enough of the information of the scene in the body, we need special optics, fisheye optics, right? We have strong occlusions because, most of the time also the body is not showing, or the camera is not showing these parts of the body which we still want to know about the action of the person. There's a nice visualization here actually from this X-ray Ego Pose paper, which shows, which parts of the body are oftentimes actually only visible from these camera views. And then I mentioned this already, specifically this challenge of very strongly distorted optics, which oftentimes hinders to use some of the strong feature detectors which we have just to off-the-shelf use in this context. Okay, many of these challenges that we have, and now let's look at how we approached some of them in our work. Okay, so let's start with methods that essentially use a single downward-facing fisheye camera, and this is mostly work done by my PhD student, Jiang. So one of the challenges we looked into is, I mentioned this, how can you get the global in addition to the egocentric pose for egocentric tracking, right? So that's a paper we showed at ICCV in 21. And the core idea here is that essentially we use, so to say, a learning-based egocentric local pose estimator and combine this with constraints also that we get from an SFM approach in a local global pose optimization step that we then use to basically position the human and refine the poses such that they are essentially aligning with the global motion, right? So that is what you see here in this work, and that's kind of the core of the idea behind it. Now, additional challenges still is that even some of the state-of-the-art pose estimators from egocentric cameras, if you take the result, and this is one of our own methods, right? If you take that result and place it into the context of a scene model, in particular in a pose like this here on the left-hand side, you see the pose in the real world, right? And it's strongly occluded, right? Because you don't see the lower part of the legs. So if you place this in an environment model, you see that, of course, the estimation you get is, non-physical. That's physically not possible because this method is agnostic to the environment, right? They could not penetrate the floor. In order to get this, by the way, this is done in our capture studio, right? So we use the exocentric cameras to get the reference pose and also the reference geometry model. Now, of course, one of the ideas that you could have is, why don't we include scene estimation as context into this, right? And that's something we showed at CVPR last year, and that gives you then a much better way of actually positioning the pose also under the strongly occluded cases in the context of the environment. The core of this approach is briefly shown here. So we have the input egocentric camera view, but then we have two branches. We have essentially a feature extractor that looks at essentially the body features from that, which we store essentially in a volumetric representation. And then we have a second branch, which is essentially a depth map based method, which is also designed such that it masks out the human in the foreground and estimates also features from the context that we reconstruct. And then we use both of these together to actually then estimate a pose in a final network that uses both of these streams, right? And as you've seen in these results, that leads to much better results also under these occluded situations. And here is, again, a visualization of this, right? So which shows that with the inclusion of the context from the scene reconstruction, so the comparison you see here is reference correct motion, or the ground truth motion is red from the exocentric cameras, and then the green is, so to say, the estimate, which works much better in the context of the environment than with the previous work. Now, one step further is something that we show here at CVPR this year. So far, all the works that I've shown are essentially only on the body joints, but they are not including the hand as well, which is very important if you're talking about using any of these techniques for action recognition, interaction with the environment, for instance. And still, we wanted to have a method also which performs well under, situations or poses where there is stronger occlusion in the environment as well, or from the body. Here's an overview of the approach. Essentially, I'm going to briefly talk through this. So it has 3 major components, right? So we have, on the one hand, we have a branch which is responsible for, so to say, the full body estimation, right? And essentially here we use a pixel-aligned 3D feature representation that we use then for a network to estimate the 3D pose. But what we want to do there is we actually wanted to use a state-of-the-art feature extractor, in particular a vision transformer, to actually extract this. Now, I talked about this before, right? So in particular, the fact that we are using fisheye distorted optics is making this hard because these standard transformers are not trained on patch structures which are corresponding to these strongly distorted images. So that's something we looked into a little bit in this work and essentially proposed a way how to be able to map these fisheye data to the space of the standard vision transformers, right? So in the vision transformer, as I said, right, we have, so to say, the tokens or the patches that we work on are not from these strongly distorted fisheye optics. In order to make the two match, what we basically do is we have this transformation step which takes the fisheye optics, the fisheye patches, and transforms them by, so to say, essentially a projection through a hemispherical proxy using gonometric projection into, well, undistorted versions of these patches. And now, basically, you're aligning the spaces of this new camera with the original vision transformer space, and then you can basically use also this architecture in the context of our work. Now, there's a bit more to it, right? So I'm not going to go into detail about it. It's also going to be presented tomorrow morning in a poster session. Basically, what are the individual steps in order to resample these patches such that they align with the undistorted space. And here's a little visualization of this, right? So it's one of the strongly distorted images we get, and essentially this on the left is the accordingly undistorted corresponding patches that we have. So that's, so to say, the body part. Actually, this undistortion step that I described is also something we use in the other component, which is the hand network part, right? So also there, we have essentially a 2-stage process. First is essentially a hand region detector, so it's 2D image detections, 2D key point detections, which we then essentially lift to 3D. And here we also use essentially the undistortion technique to get these undistorted patches that I described on the other part. Now, these are the two components. So we have essentially a hand network and a global pose network, and which we then fuse in order to get a joint reconstruction. But that's not the final stage. The final step is actually to pipe this through essentially a diffusion model, which is a motion prior that we have. And the reason for that is this helps us in particular in very strong or longer time occlusion situations. So we can use the prior of motion encoded in this diffusion model, which is trained essentially on long motion capture data, to, so to say, regularize this. And the way how we particularly do this here is we use essentially a classifier-guided diffusion sampling, because we can use uncertainty information also from the joint predictions to know which joints are most likely reliably predicted and which are not, to basically then fill in mostly those less reliably predicted joints from the diffusion prior, right? Which is then the final result of the approach. So data sets, we already heard a lot of this. I think pretty much all the methods that I'm showing here come, or most of them, with a new data set. Of course, we need also good data to train this approach, right? So we have here the Ego whole body data set, which we also, of course, make available, which has a large synthetic component, right? So we have synthetically rendered humans using Mixamo data set here, plus, real background fisheye optic images to create this more than 1 million egocentric images with ground truth poses. But we don't only have this synthetic data set, we also have a real data set, which you've seen some of the examples already because we recorded in our studio, where we have an exocentric camera system that can give us the reference images, right? Okay, and then, again, bringing all these components together, training on the new data set that I showed, we get an approach that can do things like this one. So the paper has lots of analysis, lots of ablative analysis also on the importance of each of the components. So, here just one example. I'm not sure if this can be seen very well. Actually, I think it's a bit of a contrast problem. But essentially what we showed in the paper is that, even before using the diffusion-guided refinement stage, so to say, at the end, so the per frame reconstruction with this pipeline already is actually state of the art in terms of accuracy. And it's further improved if we pipe it through this refinement stage, in particular on longer occlusion sequences, right, when you have these kneeling sequences and so on. Similar things we can also show, particularly for the hand component, right? So also here using essentially this diffusion pari for refinement, in particular also using our undistortion step and fine-tuning on this new data set that we created helps a lot with estimating the hand pose. And then, you know, what I just reported, so to say, qualitatively is also something that in the paper I encourage you to take a look at there. We show also by quantitative comparison on the data sets that we have. So, so far we talked about methods that use a single fisheye camera. And, but we also, I mean, the question is, you know, why only one, right? I mean, you know, there are other settings in which two of them, you know, gives you more context, can give you even information about depth. Even, I would say, one of the first egocentric capture methods actually used a stereo rig. And that's also something we looked into in some work we present here at CVPR. And this is work by my PhD student Hiroyasu Akada. All right, so this is a paper, well, it's a result of this paper, stereo-based input, and the estimation or reconstruction that you can get with this. Now, importantly, I think for this visualization also of the global pose is actually the ground truth pose is used, right? So this is mostly about the egocentric pose being approved. So now why, maybe a little step back, why look into stereo setups, right? I said already it gives you more information. But one dimension which we also want to investigate here is that, you know, if you look at historically how the setups that we use in our research, partially our team, but also other teams, I think it has moved. So on the left-hand side, this was one of our first egocentric capture setups, right? It was also stereo camera, but I would say in terms of practicality, this is a little bit further away from what people would probably really use in an environment, right? But over time, you know, we basically try to find setups which come closer to something that you would eventually even actually integrate in a real headset, much closer to the head, right? And then in particular, there are these works also, the Unreal Ego from our lab, which try to simulate a setup where you really have two downward-facing cameras in a headset that is much closer to your face, right? And I think that's something which we will eventually see also in headsets to come, right? So we also wanted in this research to basically give the possibility to explore settings with such cameras, which is a bit harder because you're much closer to the face, right? But it's more realistic in terms of actual feasibility of building it. So that's why one thing here is actually the data set we create, right? And we have, so to say, a simulated data set that uses this very, you know, close to the face stereo setup that simulates kind of these glasses. But we also have a real version of this, which is what you see on the right-hand side. So we built this ourselves because it's in practice it's difficult to get an actual device which has exactly this setup of cameras, or which would even give you access to these cameras for various reasons. As I said, one big contribution of this paper is actually the Unreal Ego 2 dataset, right? So the name suggests is with the Unreal Engine, 1.25 million egocentric stereo views. So it's an extension over an earlier version of this dataset that we had before. Here's a visualization of this. Right, so we have so all rendered in the Unreal Engine, ground truth poses from the simulated bodies, and then you can essentially create an unlimited realm of training data with this. But as before, we also have a real-world data set that goes with it. This was recorded in our capture stage at MPI for Informatics, where we have from the Egocentric tracking system essentially the ground truth pose. Right. There's also a benchmark website, right? So you basically can download the data set and also run your own techniques on this and basically compare yourself on this data set. But this paper also comes with an approach that actually makes use of this data. So here is I'm going to give a short overview of the structure of this method. So this is a temporal approach. So we have a sequence of stereoscopic videos that go as input. Then we have multiple major stages in the pipeline. So we have first a 2D stage where we extract with a neural network essentially features or heat map locations of the joints, which then is used also as an input to a segmentation module, which we use to segment out the person in the foreground. Now, both of this, or in particular also this segmentation, is then also used as an input to a essentially structure for motion stage that from these spans of video uses also a reconstruction environment model also of the scene. And one of the challenges there is that, sometimes, because we have difficult body poses, strong occlusions, this module, or from which we can actually then extract also depth maps, but in some poses it may not be possible to actually get depth map for difficult occlusion or various other reasons. And that's something we have to make the later stages of the algorithm actually aware of, right? So, I will not be able to go into detail about this, but in the paper we describe a bit more how we basically have the last stage of this, also make it aware of the possibility, essentially, that such cases may arise where you don't have good estimates of the depth, right? So it's the last stage, taking essentially the 2D and the depth predictions to then essentially estimate the 3D pose out of this. Okay, so here are a few visualizations of this, again, visualized in a ground truth reconstruction here of the environment where this sequence was taken. And you can see here that in comparison to the work on the left, which was, so to say, a per time step reconstruction, in particular this temporal reconstruction that we do now works much better also under these challenging poses. One thing that we also show in the paper is that, we have a very large synthetic data set, and a slightly smaller real-world data set. But nonetheless, if you take this much larger synthetic data set and fine-tune on the real data, you can still get a very big benefit from having a much larger synthetic data set, right? It basically makes the reconstruction much more robust. So this brings me to point 3 of my talk. So we have single fish eye, stereo fish eye. Another camera that we also work with, also in the Egocentric reconstruction setting, is essentially an event camera. I don't know if you're familiar what an event camera is. I show it very briefly here. So an event camera is not essentially giving you an intensity image. It's based on an intensity image, but what it gives you is a stream of events. And an event is what you see here visualized in the pixel space in red and green, is pixels where the color change, so to say, over time more than a threshold. So it's in some sense a kind of a discretized gradient image. And what's interesting about this is, if these events happen very sparsely, you can record these events very fast. So it's something that can also record very fast events, right? And I think what we have here is quite possibly the first egocentric fisheye event camera setup, right, that we actually built. And this is the data that comes from it. And we built a method here that uses this data stream to estimate also the egocentric pose from there. So what's interesting is that these event cameras have special characteristics which make them, advantageous for specific use cases, right? So on the one hand, they give you information about fast motion, so that's one thing, but they also work pretty well under low light conditions, right? Also there, when in low dynamic range situations, you can still do poses or reconstruction very well, right? Again, right, I will not have the time to go into the details of the method here, given the time limitation that I have here in the workshop. But there are multiple questions that are of interest here. One is also how you encode actually these event images so that you can make them accessible to neural network-based structures. Here's something that we use from earlier work that we did. So it's essentially normalized event surfaces that we use there. But we also look a little bit how to best make use of temporal information in order to get these estimations and also guide the network towards the most important events. So to exclude essentially background events, but use, most of the information or the important information is kind of happening at the boundary of the human, right? To basically guide the network there. Now, and again, also here, of course, we need a data set to train these approaches. And here we have, again, a combination of a synthetically simulated egocentric data set, but also a real data set with reference motions from an egocentric capture stage, which we will also make available. And I believe that's probably the first egocentric event data set that is there. So now I'm coming close to the end of my presentation. Let me, do a little bit of an outlook of other directions that, starting from what I describe, I believe in the future will be interesting. In this talk, I exclusively talked about one subset of egocentric human modeling, which is the motion estimation problem. Of course, eventually we want to use these techniques as a component to solving larger problems, understanding activities, building maybe large models that understand also the context and environment. But more concretely, improving also the pose estimation. I think one direction of work that will certainly be interesting is to combine, some of the vision-based techniques with essentially also other sensors, like, for instance, IMUs. So this was a technique we presented at SIGGRAPH last year, which allows us to do actually roaming in a very large space. So we get egocentric poses of very high quality, but we can also get global pose even on building scale levels at a very, very good quality. Now another direction which I think will be interesting in the future ties a little bit to other directions of research that in the department we are interested in particular also the photoreal aspect of human modeling. And an egocentric capture setup can be a component in an egocentric telepresence system as well. Something we also looked a little bit into. The top two works are from us, but there's also great work from the folks at Meta. And in particular, if you look at what is nowadays possible with new neural rendering techniques, this is actually an example of one of these exocentric, highly realistic avatar modeling. It's an avatar of myself, which we are going to show actually in the main conference. Right, so this is essentially a real-time driven avatar of myself. So we have 4 views at test time, and I can render this in real time from arbitrary views. Now, of course, there is no direct connection to egocentric tracking in this work, but I believe, coupling works from that domain with advances in egocentric tracking will allow us to build better egocentric telepresence systems. But it's not only this application. I think in general, combining, so to say, let's say highly realistic forward models of human modeling will help us to eventually also get better reconstruction, because they are oftentimes the key to do also self-supervised refinement when you don't have the ground truth data, because you can much better compare your model against the image data. Of course, datasets are very important, right? There's great work here in the community, right? Many people here provide their datasets. Also, Siyu already talked about this before. We also contribute our part. I showed many of them. For doing that, we also built a few capture stages here. We call this a real virtual lab. So we have a big capture stage for doing, larger dynamic scenes with 124K cameras, specific ones for faces. The latest addition to this is a full light stage as well, 4 meters, multispectral, which we also will make more and more data available. All right. So with that, I'm at the conclusion of my presentation. So if you are interested in the works that I presented, most of them are also going to be shown tomorrow morning in the main session. Of course, we show much more about the work also on the website of the department. And in particular, many of the works that I showed here are also done in the context of this new VIA Center, which is a collaboration between Google and MPI for informatics. And I thank you for your attention, and we'll be happy to take questions. Thank you.
Thank you, Professor. We have a question from the back.
What are your thoughts on the global positioning with only IMU?
Many thoughts, challenging, right? So, I mean, you will have a signal which is subject to, unreliability, noise, drift over time, right? And so you need a mechanism, essentially, to compensate this. In some sense, actually, a little bit of the insights we gained for this in the work that I briefly showed on one slide is to utilize some of the information from a camera to basically help to compensate some of these issues. So in some sense, a multimodal setup is always then best when the sensors have different characteristics, right? They are good in one space and the other one is good in that space. And then you basically benefit most from the fusion, right? And I think that's where some of this can come in. Right?
So for now, at least one camera is needed.
I would say for being able to do something like, you run for 1 kilometer or 2 through a building and still get drift-free pose estimation, yes.
So for event sensor that you use, what's the resolution of the camera and also the FOV of the camera? Because the ones that I've seen, they are usually small field of view and they're like 400 by 400.
Yeah, sure. That's a standard, right? So we modified this a little bit, I think. So this one here, I believe it had 160 by 120 or 200 by 150 or something. That's the effective resolution of the fisheye, of the event camera. Or here, yes, what was the exact? Is that correct, right? Yeah. The field of view is probably like, what is it, 160 degrees?
When you're dealing with events, it is still a bit of an open question, it seems, about how best you should represent them when feeding them to a model. It looked like you went for like an image-like representation. Is that like a time series of some description?
Yes. So there is, essentially we have, so to say, a reparameterization of the event stream into another structure that is more amenable to actually feeding it into a network. This is something we actually developed as part of an earlier work on actually this hand pose estimation with event cameras. That's where this is actually coming from.
Right. So I was wondering like how much exploration have you done in that space, and I suppose what challenges have you run into?
I wouldn't say that we basically say, we could say this is the optimal type of representation, right? So I don't think we have like an exhaustive design space analysis, right? But I think we have found a solution which has certain, advantageous properties.
One of the things we think about a little bit is how the environment constrains our movements, both the static and dynamic objects as well. How do you think about that avenue of work? Is that something that you think about, or are you working on essentially a different level?
So in none of the work that I presented here, we are using of this. We have other directions of work in which we are actually utilizing that, right? So we have also some work on hand-object motion synthesis, right, where we are using such types of constraints. And I guess your question would be, can we, combine such type of prior as well into the reconstruction task, which is an interesting idea. I think yes, but we haven't done it. Yeah.
Please welcome Hanbyul from Seoul National University. Han.
Thank you. Thanks for the introduction and thanks for the invitation. I'm going to give this talk with this title, Towards Capturing Everyday Movement to Scale Up and Enrich Human Motion Data. So maybe let's first think about why humans move the way we do. I think the first reason is to accomplish some physical goals. For example, moving object, manipulating tools, and so on and so forth. And as a human, we are very easily using the tools, even though that is some unseen tool in unseen environment. And maybe second reason is to transmit some communicative signals. So in these cases, we actually use our body motions to convey some emotions as a message and messages as if they are some kind of different channel of languages. And also as a human, we can easily encode this kind of messages into the behavior, and we can easily decode that. And obviously, teaching machines to perceive and mimic human behavior is very challenging work. And that's not only because of the hardware challenges. Even in the virtual environment, if we wanted to build a digital humans which behave like humans with this autonomy, this is a super challenging problem still. So my research goal over the last 10 years, and maybe over the next 10 years as well, is to endow machines with the ability to perceive and imitate human behaviors. And I do pursue that direction in a learning-based method, meaning we need the data to learn this kind of thing. So majority of my research is about how to collect and processing all this data so that we can pursue this direction. And we have seen lots of success in this language domain and image domain. And a major reason of this success is the availability of the data set they have. In the end, indeed, we can have lots of data set from the internet. But what about human behaviors? If we pursue similar kind of foundation models or generative modeling, indeed we do need lots of such data set in a similar scale, which is super challenging, unfortunately, because of the many reasons. So we really wanted to have authentic signals from the people in a very high quality, but because of many sensing challenges, measurement challenges, this is not an easy problem. For example, we need to handle occlusions. Getting 3D from 2D is a very challenging problem. We need to solve many scaling issues. For example, we are measuring the body scale of motions, and at the same time, we are very concerned about the small scales, such as faces and finger motions. Over the last several years, during my PhD time, I have been building this kind of system called Panoptic Studio with my colleagues here. We use about 500 cameras to build this system so that we can actually capture big spaces. The major objective of this system is actually to measure the human behavior in a markerless way so that we can actually have some authentic signals from them. For example, you can see them from 500 views. We can actually see them in many viewpoints from which we can basically collect this kind of motion data in a markerless manner. So we can capture their face motion, body motion, and finger motion, and so on. And one of the main objectives of the system was really to measure this kind of social behaviors when people are interacting each other in a natural way. You can see that we can collect their facial motions, their finger motions, and when people are talking each other, their signals are really correlated. We really wanted to capture such kind of signals. And there have been many other really great work in this domain by building a really nice system in collecting, lots of the 3D human motion data in indoor environment and outdoor environment. And there also exists lots of public data set we can use For example, in a mass data set, they consolidated all this available 3D motion data, which is about 40 hours of data. They made them in a unified format. But not surprisingly, the amount of data is not in a sufficient level. For example, I would say the amount of data we can find in the internet is about less than 200 hours at most. So maybe a similar order if I missed any recent one, which is not maybe sufficient level at all. So the question is, what would be the next? How to increase, how to scale up this kind of data toward this kind of direction. For example, we wanted to capture some large-scale data set in the wild, and especially we wanted to collect some data set in human-object interaction scenarios, which was somehow missing in the previous cases. We also wanted to collect some data in a high resolution, meaning we also wanted to collect the highly accurate finger motions as well. Maybe one possible direction is collecting the data from internet videos by somehow measuring 3D motions from, for example, existing single view 3D motion estimation. We do make lots of interesting progress in this domain. However, when it comes to the accuracy, it may not be a very accurate level yet. So with that motivation, I'm going to introduce two efforts done in our lab. The first approach is to collect some long-term in the wild capture using a very lightweighted mocap system. And then we're going to introduce our para-home system. So let's maybe get into the first one first. This one is done by my amazing student Ziwei. The paper is titled like that. The major goal of this system is really to collect every day of our life in a 3D motion data. For example, somehow we can wear this system for really long time, 24/7, so that we can do some kind of life logging thing in the case in a motion capture format. And one possible approach we can try is maybe via this wearable mocap. But the problem is the wearable mocap is in fact really expensive, and that's really inconvenient because you may need to wear this suit or you may need to attach lots of IMUs. So to this end, our system looks like that. We only use 2 smartwatches, basically Apple Watches, on one per each wrist, and we use one Egocentric camera. So in our system, we use the GoPro camera because unfortunately we couldn't get the area glasses, but we will maybe try if that can be supported. But anyway, our system is very easy to use because anyone can easily obtain this kind of system. So as you can see on the left, that is Jiang, who is wearing the system, which looks just natural. And as output, our system can infer this kind of full body motion as shown in this example, although the signal is extremely sparse. So our signal is only the videos from Egocentric camera and only the IMU signals from 2 smartwatches. So let me just very briefly introduce our pipeline due to the time limitation. So from the video from the Ego camera, we can basically do the structure from motion or SLAM so that we can get the point cloud and at the same time the camera positions per each frame. That is basically the head pose. And in the end, we combine this head pose information from cameras with IMU signals. However, they are not straightforwardly combined because their coordinates are different. So we need some calibration process in advance so that we can align their coordinate system. So it turns out how to represent the signals itself is a really important problem to solve this correctly. First, we need to normalize the signals. So we have the head poses from cameras, and we have IMU signals, basically the orientation and acceleration. And we input the signals in a sequence manner using the slide window fashion. So we use the first frame as the origin, and all other head poses are somehow normalized with respect to the first frame. But if you use this normalized coordinate, which is very common in any neural network approaches, very important information is, global information is basically missing. For example, if you think about the standing guy and the guy who is sitting, basically their IMU signal would be very similar because there's no global information at all. So it turns out adding some global coordinate system is very important. And in our case, we added the up vector, the global orientation up vector. And additionally, we compute the height of the person at each time instance so that we can somehow get the status of the person's motion, which is, it turns out, very important. I'm going to explain a bit detailed that later. So to this end, we combine all this information and we just use a sequence-to-sequence kind of network, transformer-based, to infer this kind of full body motion. Yeah, I'm not going to get into all this detail of the network architecture, but basically we use a transformer-based sequence-to-sequence model. As I mentioned, imputing the global information is important. So we need to compute the height of the head pose. And that basically means we also need to infer the flow level so that we can compute the height. But if you actually think about the case where the person is going maybe in the wild situation, flow level can be also changing. So in our case, we need to actually fit this local floor level information using this kind of local plane fitting information. Using that information, basically we can compute the head height. That is the input of our network. That regression itself produces already pretty decent kind of output, but we can do additional refinement. So especially when you actually think about the hand localization quality, because of the ambiguity, IMU only provides us the relative information. The localization quality may not be sufficient. But very important Q we can further leverage is basically the vision Q we can obtain from egocentric camera, which is not always available, but sometimes, especially in the manipulation task, we notice that people is actually focusing on the target object, which when we can basically get this kind of additional Q. So we use such kind of a Q to further refine our motion capture output. And another very interesting example is assuming that this kind of method can be applied for multiple people, where multiple people are wearing the similar kind of setup, and our goal is to obtain their motion data all together. Maybe we can use one person's vision cue for another person's motion refinement, which is also not always usable, but if that is usable, then we can use that additional information. I'm gonna maybe omit the details of this refinement, then directly jump to the result. So on the right, you can see the egocentric view, and you can see the full body motion. So in this example, actually, we go outside and just move around in a very big kind of spaces. You can also see this bird's eye view to see how big the space is. The person is moving around. It turns out locomotion estimation is quite relatively easier. Localizing the hand in a precise way is much harder. This is another example in the case of manipulation task. You can see the video and 3D motion. Another example. As I mentioned, if you use this kind of devices for multiple people, basically we can collect their motions all together. And because we are using structure from motion, we can register their camera space in the same space. So this is an example. This is another example. So our hope is if we can distribute this kind of open source, people can use this open source so that they can collect every day of their motion. They can maybe upload this data to internet, which can be usable for the processing. Okay, that part is for the in the wild motion capture part. And I'm gonna jump to the next one, which is ParaHome. ParaHome system is led by Jeonghan Jisoo, my amazing student. And the output of the system is something like that. So we have this kind of home kind of environment where we have all this furniture, small object, from where we can basically capture the human body motion, finger motion, and human object interaction. So you can actually see that all the object in the scene is actually in a parametric form so that we can actually remember the status of each time. So the goal of ParaHome is really to collect this very natural human object interaction. Of course, there is just other really nice work, but most of them are really focusing on human hand and object interaction in the standing pose. Compared to them, our goal here is to make some more natural home environment so that people can interact with many objects freely. For example, in this example, we ask the person to do the following instruction: put the sliced food into a pan. Given this instruction, they can just move very freely. They can interact with multiple objects and so on. And basically, we have this paired instruction per each scene, which will be also available. So given each instruction, they can just move freely based on the instruction. So what's new in our data set? We try to have some natural room setting for more interesting kind of data collection. And we try to capture dexterous hand manipulation and body motion. And all of our objects are in an articulated form so that we can actually remember the status. People can move around the room, and all the data set is annotated. So let me just show you the brief overview of our system. It's another multi-camera system, and my student is basically struggling with the same issue I had during my PhD, which is really fun to see. I believe that is really rewarding, really rewarding. So we use about 70 RGB cameras to capture the movement of the object. You can see lots of markers. I'm going to explain why we have such markers. And for the person, basically we have this IMU-based motion capture suit. So the main reason of having this wearable motion capture rather than marker-based motion capture is really for handling occlusions. So this wearable motion capture is basically macro occlusion-free, which is really needed for this kind of human-object interaction. However, for tracking object, we need to have multi-cameras so that we can collect this kind of 3D object movement. So the main issue of building this system is basically the discrepancy of the sensors. The mocap is from wearable mocap sensor, and 3D object movement is from multi-camera system. They are not sharing the same coordinate, and so on and so forth, so we need to handle such kind of thing. So this is the view from 70 cameras. You can see the person is moving, object, and so on. Oh, another very important thing about our marker is we intentionally put the marker above the surface of the object because during the interaction, they easily hide or occlude the markers on the surface. And all of the objects are 3D scanned so that we can build this kind of parametric model for every object. So each object movement can be parameterized. It may have one parameter if it has one door. If it has two doors, it has two parameters. Capturing the object movement is quite straightforward because we have markers. So given attract markers, basically we already have pre-computed relative location and orientation between markers and object. So we can just place the object on the right location, like this. As I mentioned, there is just some issue between two different sensor types. So one very big issue is the mocap from the wearable mocap sensor is not, doesn't provide the accurate length of the skeletons. So we need to have some calibration process to figure out such things by combining the multi-view camera measurement and mocap measurement. I'm going to skip the details. As some additional output, we can also get this kind of contact information or the distance between object and fingers. As you can see, people just can move whatever they want based on the instruction. Of course, when people are performing this kind of behavior, there is just some order of motion. For example, you need to open the door and take away some object and close the door. We, as a human, we are very we are familiar with all these orders, but learning this is not an easy problem for the machine. So this guy can turn on the stove and open the door, cover the pan, and so on. This is another example. Okay. So very interesting thing is, given the same instruction, the behavior of the people are very varying, very diverse. So our goal here is really to somehow model such diversity given the same instruction. So you can see the instruction on the below, pouring water from kettle to the cup, or put laundry in the washing machine. You can see the motion of the people are very different. And this is cut the food on the cutting board. So we are currently finalizing our processing, so hopefully the dataset will be available during the summer. Currently, the demo version is available already, so please feel free to take a look at, and feel free to send us any feedback. And then for the sake of connecting this dataset to this Egocentric workshop, basically we can synthesize the view from Egocentric view by just considering any pseudo camera positions. So given this data set, maybe we can pursue many interesting new research directions. So given that we already captured both object movement and human motion, our first goal is to somehow model the correlation between the object movement and 3D human motion. For example, in this example, the input is desired object movement, and output is the expected human motion to make such kind of movement. Some example output here. To make this kind of object movement, our trained model can infer the corresponding human motion as the output. Again, object movement is the input. Basically, they're changes of their parameters because everything is in a parametric space. We can infer the corresponding human motion. Of course, there should be some diversity here, so maybe we can use any generative model, diffusion, or any other things. This is another example. The gray is basically the input, some status of the environment, and the magenta is the expected human motion inferred from our model. And in this case, we just provided everything, including the body motion. And finger motion, corresponding finger motion can be the possible output in this kind of case. Right, I have introduced both of our effort, and hopefully once our data has been collected, we're gonna release all of them. For the remaining time, let me just briefly advertise my other work, assuming you guys are also interested in human digitalization. The first work presented in this CVPR is basically layering SF from 3D scan. So input is a single 3D scan, and given a prompt, basically we can separate them out, the selected head and the remaining part. Of course, if you detach this selected part, the part inside is basically blank. So we need to fill in the geometry and texture as well. And that can be done by diffusion model. This is another example. If you choose to separate the shirt, basically you can separate them out. Our approach can be applied in a recursive manner. For example, you can separate head first, separate jacket, separate hoodie and gloves. And really cool thing of our output is everything is actually parameterized in the canonical space. That means you can basically detach some part and reattach that part to another person. And all of our output is in an animatable format because they are represented in the canonical space paired with SMPL model. So feel free to take a look at more in our poster session. This is another one, sorry, one more, two more actually. Yeah, this is building a generative model, especially personalized generative model, so that you can substitute or manipulate some subpart of the face, which is done by Hyun-Soo Cha. The name of the paper is Pegasus. This is another one, which is to reconstruct multiple people from partial 2D glimpse from monocular videos. And to fill in this missing part, we also need to use diffusion model. All of our work is basically done by my amazing student. I'm just advertising this. So yeah, thanks a lot for your attention. And happy to take any question. Yes, Aisha.
Very nice work.
Thank you.
So for the human behavior capturing and understanding, right, you have two ways to capture behavior. One is very fast sensor, one is
Exactly, yeah.
And I'm wondering, what's your thought on leveraging 2D information, 2D videos? There are also behaviors.
Exactly.
Modern human behavior
Yeah.
is just based on 2D videos.
Right. So that's really important and interesting question. And I do believe in the end we need to fuse both information together. So my inspiration is actually originated from HMR kind of work where basically we use 2D key point as a really important input and at the same time 3D existing work. Obviously the amount of 3D data is never sufficient, but by combining all this together we made really nice system. I believe we can maybe do that very similar kind of approach at the very beginning by combining 2D video information and existing 3D data set together. Yeah, yes.
Do you have an expected release time for the Parahome data?
You need to ask to my students over there. It's really up to them. Hopefully within 1 month, 2 months, 1 month. Okay, thank you.
I have a question. It seems like everyone who's collected egocentric data suffers the same challenges, perhaps. And I'm just wondering if you consider the data collection to be the challenge that if you overcome that, that will provide the solution, or if there's new algorithms that need to be discovered in addition to data sets, maybe you could just talk about that.
Yeah, that's also a really great question. I think over the several years, we really try to make really nice representation to solve this problem. And maybe this is a really good time to reconsider the data set part. I believe that provides us some additional chance to reconsider the problem. In the end, both of them are important. Yeah.
Everyday data capturing is for how much frame rate?
The frame rate is really dependent on the egocentric camera because I think that is the major bottleneck. I am not sure about the number. There's my student. I think that would be 30 frames per second. Around, yeah. It's really dependent on the system, yeah. Yes?
Just piggybacking on the earlier question, what does the role of orientation and placement of the cameras with respect to the head affect on how it is?
So first, it provides us the global trajectory of the body. Second, the orientation is really important because IMU only contains this relative dynamics. It doesn't provide any global information. But if you actually think about the orientation of the up vector and the height, it actually provides lots of things about the status of the motion. So without the camera, we believe it doesn't work well. So only IMUs may not be sufficient.
And one last question would be like so thing is about the legs, like how were the legs estimated at this point? Because the sensors were in the hand, on the hand, and you had a camera adopt. So how does the motion of the hand, like the strides, affect
Yeah. So it's really ambiguous problem in the end because, for example, if you're just still without moving anything and sitting down, there's no difference in the IMU side. The only cue we can maybe use is the height information, right? That is one additional cue. But nonetheless, the surprising thing is when you are doing very usual kind of motions like locomotion, surprisingly the arm movement and leg movement are really correlated. But if you do some random motion, although I'm standing here, maybe I can move in a different way, right? But if you do this unusual motion, obviously this is a very challenging problem.
Thank you for the presentation. So in your first work, you tried to use like glass smartwatch instead, and how did you perform it?
That's an excellent next direction. I'm encouraging my student to pursue that, but she wanted to do another problem. So you can maybe solve the problem. That's an excellent question, yeah.
Hi everyone, my name is Lingni. I'm a research scientist. Today with my colleague Yuting, we're going to talk about Project Nymeria, understanding human motion from egocentric data. So we'll be presenting the team effort from Seoul and Gemini at Meta Reality Labs Research. This is in collaboration with NTU, Stanford, and the University of Tübingen. So let me start by motivating the problem of egocentric motion understanding with this video. So what you're seeing here is actually me wearing a pair of Project Aria glasses, walking around a building and trying to interact with the environment. I'd like you to first focus on the RGB stream, which capture my egocentric perception, and notice that how sparse it actually observes my own body motion. However, I bet your brain will probably piece out what I'm doing in the environment. And the question is, if your brain can piece it out, can we actually train an algorithm to be able to do the same? What I mean is not to just predict one single state of the human motion, but rather a probability distribution that represents all the possible states that respects the observations from your egocentric vision. And furthermore, can we even go beyond by predicting the parametric motion states, which are mostly designed for computers and algorithms to interpret it? What about with direct predicting into the natural language space, which is more for humans to actually understand? So about 2 years ago, we started to look into this problem, and we realized that actually the biggest bottleneck to this problem is about the data. So throughout this workshop, you have seen a lot of people present various types of data sets. However, we'd like to remark that most of these data are either isolated motion without egocentric data, or having limited scale or diversity, and often staged with a lab setup or missing certain important annotations. So arguably, build a dataset that with all the desirable features to study the problem of egocentric motion understanding is a very challenging task by itself, which involves soft motion capture in the wild, synchronize multiple devices, processing the data properly, as well as produce useful annotations. And above all, you need to do all of this robustly at a scale. Now, with all these challenges in mind, allow me to introduce you the Nymeria dataset and how we build it. The Nymeria dataset is a massive collection of human motion in the wild, captured with diverse activities performed by a diverse group of people at diverse locations. It provides multiple multi-modal egocentric data as well as full-body ground truth motion. To help you understand the quantity and diversity, in this video, I show you a random 100 snippet from the Nymeria dataset. So obviously, there's a lot that is going on, so let me help to break it down for you. First, we use Project Aria to record the egocentric multimodal data. This includes capturing the cameras, the IMUs, the eye trackings, the audios, and etc. Now, you may have heard Aria machine perception services. This is a great tool that provides us with 6-off accurate device tracking, the semi-dense scene point cloud, and the gaze with depth. Next, we actually modified the Project Aria glass into a wristband form factor to capture the same good stuff from your wrist. The reason we do this is motivated by to resemble the future wearable wrist devices, as well as to obtain the accurate wrist motion so that we can better constrain the body tracking algorithms. Now, for the motion capture, we actually use the Axon's mocap suit to obtain the full body motion in the wild. Furthermore, we retarget this kinematic body state into a full parametric human model powered by the newly open-sourced meta momentum library. Later, Yuting will talk you in depth about the momentum library and how we did the motion retargeting. For now, I'll mention that we optimized the global body tracking to align with the same coordinates of the Aria device. With that, we'll also add an additional observer who also wears the Aria glass to capture the action from third-person perspective. Now, let me stress that all of the devices, the Aria, the M-Aria wristband, the motion capture suit, are fully synchronized and localized in one single metric world. Last but not least, we actually show the synchronized first person, third person, as well as the 3D human rendering to human annotators who write dense descriptions about the body motion, the atomic action, and activity summarizations. So now I show you we have a solution to solve the technical challenges. Let me walk you through how we design the content of the data to capture the rich diversity of everyday life. To start with, we come up with 20 scenarios for the daily motion, such as doing exercises, playing games, doing houseworks, and social interactions, etc. Each of our recording is about 15 minutes long, and the scripts are only provided to participants with high-level descriptions, leaving plenty of room for us to capture natural, authentic motion and interactions. Showing you in this video is the same person perform 6 different activities. Next, we actually scale up along the participant dimension. We recruit 264 participants to capture how different people perform the same type of activity in a slightly different manner. While we capture the diverse participants, we made sure the demographics is balanced with respect to ethnicity, the gender, the height, the weight, as well as their age group. In this video, what you see is 6 people doing 3 sets of activities. Next, the diversity is about the location. We rent 47 houses to do the data recording. Showing you here are 4 examples. These are single family homes. Most of them have garden, multiple rooms, multiple floors, and definitely a different layout. At each location, we record about 4 to 15 hours of data, and once we overlap all the trajectories captured at each location, you start to see how dense the motion is. And if we further zoom in on these locations, it's interesting to see that the natural cluster starts to merge, which represents the spatial distributions of people's head and wrist. Now, in addition to these family homes, we also capture a large open space campus, which has a multi-story building, a cafeteria with outdoor patio, a parking lot, and several biking and hiking trails. We captured 20 hours of activities performed by 40 participants at this site. Now let me play this video to show you how different activities participants do over this open campus site. Okay, now you have learned how our data set capture the rich diversity of everyday life. The story actually doesn't end here. We add motion language descriptions to connect human motion understanding with natural languages. To do this, we actually develop a hierarchical annotation schema to describe motion at different granularity. So our finest annotation is about motion narration. With this task, annotators segment the video into short clips, about 5 seconds each, and they focus on writing descriptions of detailed body postures, how they interact with the environment, with people, and what they are focused on. Our annotators write descriptions for about 39 hours of motion. This contributes to over 100,000 sentences into over 2.7 million words. And if we visualize these distributions as a word cloud, you see there's a lot of descriptions about people's left, right, arms, legs, hand motions. Our next level annotation is about atomic action. These are simplified tasks where annotators are encouraged to use verbs to describe how the action is and also how the interaction is. Now again, our annotators add over 200 hours of motion narrations. This amounts to over 170,000 sentences written in more than 5 billion words. If we visualize the word cloud again, you see actually the most frequently mentioned two words are right hand, which maps to how naturally people interact with their environment. The most coarse annotation task we have is called activity summarization. With this task, annotators create longer time span segments to write summaries about the scenario. So typically, these segments are 15 to 30 seconds long, and are written in one single sentences to describe what is the participant doing with the environment. Again, if our annotators add approximately 200 hours of motion narration here, and they are written in over 22,000 sentences and about 0.45 million words. And in this word cloud, you see the most prominent word is actually peer, which stands out as how people interact with with the other participants or with the other moderators happened in the data collection. Now, if we put them all together, we'll see we annotated over 230 hours of motions. This offered more than 300,000 sentences written in more than 8 billion words. Now, this brings me to the conclusion of our dataset. As it stands today, Nymeria is the largest dataset of human motion in the world, captured with more than 300 hours of daily motion from 246 people. It is also first of its kind, captured with multiple multi-modal egocentric devices, fully synchronized and localized in a single metric 3D world. It is also the largest dataset with in-context motion language narration. And it's important to note that this dataset is created with strict privacy and ethics in mind. Now, with this quantity of data, you only start to imagine what type of research the dataset empowers. Of course, we can use it to study the problem of egocentric motion tracking to understand motion synthesis and activity understanding. But we believe these old things scratch the surface of the full potential. So before I ramp up, I actually want to share you an example research enabled by Nymeria. It's called HMD2. At its core, this is a diffusion model trained to track and synthesize body motion from a single area input, using its 6-off trajectories, the RGB videos, as well as the semi-dense point cloud. Now, as I play the video, what you are seeing here is the inference of the model test on unseen people perform activities at unseen locations. And let me stress that if you focus on the RGB videos, for example, the kicking soccer ball on the top right, you will see how little information the RGB videos captured about one's own body. But nevertheless, trained with a large quantity of the data, the network is able to make very reasonable predictions about the body motion. Now, A majority of this work is actually about retargeting the motion into a full parametric body model. And with that, I want to share the stage with my colleague to tell you the secret sauce how we did this.
Hey, my name is Yuting, and I'm a research scientist working with Lingni together to produce the Nymeria dataset. The most important aspect of egocentric human motion is to have very highly accurate motion ground truth. So what I'm trying to convince you in this talk is of the quality of our human motion ground truth and of the parameter space that it offers you in terms of supporting the learning algorithms. So we open source all our processing code as well as the human model and a library. So please check it out. So the first question you may have in mind is, why do we want to use our custom library and human model for this effort and not use, say, SNPL model like everyone else? Let me try to explain what features we are looking for and why we are doing this. So first of all, we would really want a parameter space that's anatomically accurate as possible, but at the same time is still simple enough for efficient compute and easy manipulation. We would also really like this parameterization to be semantically meaningful so that it's interpretable and editable. What we also offer is a differentiable inverse kinematic solver. When I say it's differentiable, it doesn't mean that it gives you like gradients with respect to the pose. What I mean is that we can differentiate through the optimization process. So we give you gradients of the optimal solution of the IK problem with respect to your initial conditions or parameters in your problem formulation. For example, the weights of different objective functions. So if you use our differentiable IK layer in your model, for example, then you can have your earlier layer predict these parameters or predict the initial condition, and then you can differentiate through the optimization process through your network layers. And then we also offer a trajectory optimization solver, so you can solve it frame by frame. You can also solve an entire sequence at the same time. And of course, kids these days, they do not use C++. Everyone uses Python. So we offer Python bindings, which is fully compatible with PyTorch. And we use PyTorch tensors for our underlying data structures. But if they are interested in learning about C++, our core implementation is in C++. We try to strike a balance between the performance, but also the understandability of the code. So we try to keep the implementation as textbook or interpretable as possible. And I really believe that this would be a really nice code base for professors to teach fundamentals of character animation in your graduate class. Our code has been extensively tested and used in production, so you should feel comfortable using it and know that we try our best to make sure there are no bugs. We also support industry standard data structures, data formats such as GLTF, FBX, and C3D for marker data, so that it's really easy for you to visualize your data or exchange your data with other projects or other research groups. And there are many just standard tools that you can use and download for free on the internet. We want to also open source unique and interesting data sets such as Nymeria that uses our tool chain and uses our human model, because we really believe this is a meaningful modeling or parameter space that could really help advance human motion understanding. And this library has been extensively used internally in Meta, so we have a very vibrant and active user base. It's used in both Meta's production work in the Quest and also in a lot of the Meta research publications. We couldn't really say it out loud until now that the library is open source. So I hope that you will see more of the reference to this library, and we really hope by open sourcing this effort to encourage the community to give it a try and really kind of advance the field of human motion with a more meaningful human motion representation. Okay, so what is this about that I try to sell you? For the interest of time, I can only explain in a bit more detail of the human model and the inverse kinematics solver. But please explore the code base and try to find out how it may fit your project. So comparing to the SMPL model, we differ in a few significant ways. So first, we want to make sure all our joint locations are in anatomical accurate places. For example, if you compare these two models, we have the bones that really correspond to the collarbones on the skeleton, versus for the SMPL model, one of the origin of the shoulder joint is somewhere inside the body that's not quite accurate. We also have a much more accurate spline curve that follows the real skeleton curve. And there were other features that I will dive into just in a little bit. Also, if you look at the definition of the local coordinate of the joints, we make sure all the coordinate axes are really aligned with the bone directions. What it offers you is a very meaningful parameterization of the rotation space, versus in SMPL, all the local coordinates are oriented with the wall space that does not change with the bone direction. So with our bone-aligned axis definition, what we can also offer is a really easy left-right mirrors by changing the direction of the joint that aligns with the bone, whether it's along the joint or opposite to the joint, so that with the same numbers, same rotation numbers, you can apply it to the left side and the right side to give you a mirrored pose. We also have a lot of what we call helper joints to improve skinning. So in SMPL model, they offer pose-dependent shape correctives in order to correct for artifacts in linear blend skinning. So we also need pose-dependent shape correctives, but at the same time, we actually employ a lot of tricks to improve skinning just by using more joints. And I will expand on this a little bit later. And finally, we also offer LOD meshes, so you have different mesh resolution for a different purpose. If you just care about the motion and you want a nice mesh for rendering, maybe you can use a lower level mesh. Or if you really want to fit a high resolution model to your 4D scan data, then maybe you want to use a higher level LOD. So this set of features are actually pretty standard, industry standard for a visual effects industry or the game industry in character animation, but they may not be as well known in the computer vision community. So we really hope by open sourcing this library, we also introduce some of these concepts to really help the computer vision community to understand better the knowledge that has been accumulated in the field of computer graphics. So in addition, we also offer full hand skeletons that you could also manipulate and pose. We offer joints on the jaw and the eyes. We also have blend shapes, so just a standard package of the full human skeleton. So what is special about our parametric model? So we parameterize every joint by 7 numbers, 3 translations, 3 rotation, and 1 uniform scale, which is quite standard. But what is nice is that because of the way we define our local axis, so the translation aligns with the bone length, and the 3 rotations have their semantic meanings that you can manipulate. For example, you can apply constraints to say this joint can only have a certain type of rotation. So we also introduce a different parameter space we call model parameters. What it does is it's a linear transformation to the joint parameters. And we call this linear transformation the parameter transform. And I can offer you a few examples of what are possible parameter transforms. For example, you can just use an identity transformation, which means the 2 sets of parameters are the same. You do not want to impose any priors. But you could also just select only the rotation degrees of freedom and say, my model can only do joint rotations. You can also compute PCAs of your pose space, so that would be your parameter transform, which would be a dense matrix. But more importantly, we have a manual definition of this parameter transform that's more akin to the rigging concept in computer animation. And that's what I'm going to explain a little next. So one example is that when we twist our lower arm, we don't actually twist from the elbow. Our elbow only have a bending degrees of freedom. All the twists originate from the wrist and by the ulnar and the radius joint rotated about each other. So that's how we model it with this parameter transform. So we have the twist, which correspond to the X rotation on the wrist. And then we only have the bending on the lower arm, which is the elbow. And then we have a set of what we call twist joints along the lower arm axis. And then we have a parameter that gradually distribute the twist degrees of freedom along the joint so that when you rotate, it has this nice skinning effect. And then this is just a really simple linear relationship where we have joint parameters on the left and we have model parameters on the right related by linear coefficients. So here's how it looks like. In the interest of time, this is another example of the spine where we only use 2 parameters to control 4 joints to have a nice spine curve. So we also have a different set of model parameters that only controls the identity of the person, which are time invariant parameters specific to a particular model. So they consist of translation degrees of freedoms of a bunch of bone lengths and a few scaling parameters for the global scale and for the any factors. We also have fingers and blend shapes that are less relevant for a Nymeria dataset. But the difference with the SMPL model here is that our bones are disentangled with shapes, meaning a person can be independently tall or short versus big or small, and they could independently have a long and skinny arm or a short and a bulk arm. So for the interest of time, I will skip the visualization and go to our forward kinematics formulation, which is really straightforward. So we stack the translation, rotation, and scaling transformations. They are 4x4 affine transformations together to represent a local transformation of the joint. What I want to point out is we have the pre-rotation, which is the rotation offset between 2 adjacent joints, but we do not have what's called a post-rotation, which would have been applied after the Rx, Ry, Rz rotation. And this formulation is again an industry standard. And then if we want to compute the transformation of the world, we just stack all the local transformations along the kinematic chain. And then we can rewrite this as a parameter, as a function of the model parameters. And we separate the model parameters into the identity parameter, which is time invariant, and the post parameter, which depends on time. And then the blend shapes apply at the rest pose. So that's our model. And now let's talk a little bit about what Xsense provide us. So Xsense records IMU signals on the body, which gives you the angular accelerations, which can be then integrated to get the angular velocity and orientation. And Xsense take that information and through their proprietary solver, they give you the joint position and joint angles of their own proprietary skeleton. But in addition to that, they also provide a set of anatomical landmarks on their skeleton that derive from the poses they solve for. And then they provide a few standard file formats as well as the proprietary formats. So in order to process this data, we do not want to directly use the Xsense skeleton or their joint angles because it's not in a representation that we feel like could help us process the data. So what we do is we use the anatomical landmarks from Xsense, which they can provide as C3D data, which is a very standard optical mocap format that you would get from other optical mocap software as well. So what we do is we have to define the same set of landmarks on our own model, and then these landmarks are defined as a offset and a parent joint. and this have to be defined manually. And then this parent joint does not have to be a bone. It could also be those helper joints that help with skinning. And the effect of that is you get a little bit of skinning effect for very low compute costs. And then we just use our forward kinematics transformation to compute the world position of this landmark. And then we get the position from XSense for every frame, and then we just compute the error, which is the error term that we want to minimize in our optimization. So we just put it all together. We sum up the errors for all the landmarks along all the frames, and then we solve all the unknowns, including the identity parameters, the pose parameters at every frame, and also the offsets for every landmark. So in practice, that's a huge problem because our sequence is usually 15 minutes long and 240 hertz. So we can just pick a small subset to only solve for the time invariant parameters, and then we can solve for the poses for the entire sequence. Additionally, we provide a lot of other optimization terms such as collision and smoothness that you can use in the problem. We also implemented this generalized L2 loss that allows you to use a fractional norm as well. So this is an example sequence of what we solve for. So the red skeleton is our result, and the blue skeleton is stripped from XSense. And you can see those small dots are the anatomical landmarks that we try to match. So we don't match joint by joint position with XSense because their skeleton are not very anatomically correct. But we match their anatomical landmark positions, which means that's where they intend to be more accurate and more human-like. So this is just another visualization of the same thing, but with a mesh, just to show that it works. And because we use standard formats, so you can use any standard tools to visualize. This is just like a free web browser. So that's a quick rundown of how we process the human motion data. And I believe there are a lot more useful features in our library that I hope you can find time to take a look and find it useful.
Thanks a lot for the talk. I didn't get the part why do you have inverse kinematics. Is it because the XSense skeleton is different than yours?
Yeah, so the XSense provides a skeleton, but it's a very robotic-like skeleton that does not match the human wow. And also, it's really difficult to fit a nice human mesh to their skeleton for visualization purpose. So what happens is it looks really nice on their robot character, but as soon as you try to drive a natural human mesh with their data directly, then you will see all kinds of artifacts.
Now let me please welcome Professor Karen Liu and Jiaman Li to the stage to present their talk.
So this is a Jiaman's talk. I'm just going to set her up. Just give you a little bit of background why we are interested in egocentric perception for human motion synthesis. So when we think about human motion modeling, usually this is our ultimate goal. We want to be able to mimic what actually happened in the biosystems. Like, for example, we have this sensory actuation process, which contains three processes. You have a perception, decision-making, and actuation. In computer animation, usually we focus on decision and actuation, and we make some really wild assumptions about perception. Oftentimes, we just assume that someone will give us something, like high-level commands, and we'll just do the job. It works out okay most of the time, right? Like, there are definitely applications where the commands, the controls are done by some other procedures. The character doesn't need to perceive the world by itself. But one of the biggest problems we noticed that these agents that we created, they're good at actuation, but they lack the general decision-making abilities. And about 5 years ago, we made a bet. We hypothesized that the only way to get the general intelligent decision-making ability is when we start taking seriously about perception. The character has to be able to perceive the world in the multimodal perception fashion and be able to reason about the world. And then one interesting question is, why don't computer graphics people care about perception or computer animation specifically? And I would say the reason is because the world looks like this. It's just an empty space. And most of the time we care about not falling on that ground, right? Just being balanced is hard enough. But as we move toward contextual animation, contextual motion synthesis, where the environment becomes a lot more realistic, we really have to start thinking about perception. And that's where computer graphics should partner with computer vision. And there's still a difference, right, between computer graphics and robotics. For example, even though the world is complicated, we still have access to those privileged 3D information. And then the question is how much 3D information you want to use. We argue that you have to, there's no black and white answers. But one thing we believe is that we need to be able to model egocentric vision. Even though it's, it could be a 3D vision, but it has to be egocentric. So one interesting thing we found, this was 4 or 5 years ago, that we were in computer graphics. We're always very good at producing perfect animation, but oftentimes the real behavior is not perfect, and the reason is because our vision is not perfect. If you want that kind of realistic, imperfect motion, we have to model perception. And this is another project we did in the past. This is also a long time ago. If you want to have this kind of searching behavior, like you ask your agent to look for a pair of glasses in this apartment, you cannot just give it the privileged information because the character will just go straight to there, right? So you want a character to be able to use its own, limited sensing capability to reason about the world. We also did something that depends on egocentric perception for manipulation of soft materials. And this is also something we found that RL learns so much better if it's egocentric. So after a while, we realized that, so all these projects that we did, they don't look impressive because they're 5 years ago, but another reason is because they do not depend on data. These are all just physics and RL, and try to explore, what behaviors that would actually achieve the reward. But after a while, we feel like we kind of hit the wall. We need data, and that's when we start thinking about how do we collect this kind of data that have a pair observations and actions. And this is something we did with a combination of motion capture system and virtual reality. So here you have very detailed actions paired with the egocentric perception. And then we also think about, egocentric is not just about vision, right? It could be some other type of sensor, like inertial pulsar. This is a work, transformer inertial pulsar is a work that's done by my student Yifeng. I think he's somewhere here. And Yuting, of course. And Tom as well take this project to the next level to create a diffusion model that can handle different number of IMU sensors, different configuration as well. So I'm going to stop here because this, my student Jiaman today has a lot of material to talk about how we actually leverage egocentric perception. Jiaman, do you want to set it up to actually do motion synthesis even with the object of manipulation?
All right. Hello, everyone. I'm Jiaman, and I will introduce our recent projects about egocentric observations and human motion. So I will first talk about how do we perceive human motion from egocentric observations, including estimating human motion from egocentric video only and estimating human motion in interaction from the egocentric observations of the object. And then I will introduce our recent project, contextual interaction synthesis, which enables us to use a motion synthesis model to generate egocentric observations. So basically the opposite direction. So first, let's talk about human motion estimation from egocentric video. So this is a work published in CVPR 2023. And in this work, we aim to estimate full body human motion from egocentric video. And egocentric video is captured by a front-facing head-mounted camera, as shown on the left. And we learn to predict the possible human motion corresponding to the egocentric video. There are two major challenges.
First, collecting a large-scale dataset with paired egocentric video and ground truth full body motion is very challenging. And existing paired datasets have limited scale and motion diversity. Second, for an egocentric video, the corresponding human motion could be this, or it could look like this. So there's this significant ambiguity in the mapping of egocentric video to full body pose, since the full body is usually unobserved in the videos. And there are a few datasets with paired egocentric video and the full body poses. However, this dataset has limited scale, and they have limited scene and motion diversity. For motion, they usually just local motion, like walking and running. But we do have more accessible paired data with egocentric video and head poses, such as Ego4D or EgoXO4D. And we do have large-scale motion capture datasets like AMAS, which contain both a head pose and full body poses. So to overcome the challenge of limited paired data, we propose a decomposition strategy and develop a two-stage framework with a head pose as an intermediate representation. First, we estimate the head pose from egocentric video. Then we feed the predicted head pose to generate full body poses. So with this decomposition, we can train these two stages separately without the need for paired datasets with egocentric video and full body human motion. So for stage 1, we only need data with paired egocentric video and head pose. For stage 2, we can train our model on any motion capture data only. Specifically, in stage 1, we first extract the head pose using the state-of-the-art monocular SLAM. However, there are two problems with the head pose from SLAM. First, the gravity direction is unknown. Second, the scale is different from the scale of the real world. Since the desired head pose for our stage 2 requires the head pose to have the same scale and gravity direction as the real world, we propose two learning modules to address these two problems. So first, we propose a gravity net to estimate the gravity direction vector given head translation and rotation extracted from monocular SLAM. And we use AMAS dataset and apply random scale and rotation to the head pose to train the model. In addition, we propose headnet to estimate the distance scalar value between every 2 steps, and also angular velocity given a sequence of optical flow features. So this model can be trained on datasets that contain both egocentric video and head pose. So to summarize, in our stage 1, we propose a hybrid approach for head pose estimation. We first extract head pose leveraging the monocular SLAM. And then we use gravity net to predict the gravity direction vector. And with the predicted gravity direction vector, we compare with the real gravity direction vector, and we can compute a rectified rotation matrix. And then we apply this rotation to the raw head translation from SLAM, get the rotated translation. Then we input optical flow features to headnet, predict the angular velocity and the distance scalar values. Based on the predicted distance, we can rescale the rotated translation and produce our final head pose in this stage. And here are some quantitative results of stage 1. So compared to monocular SLAM, our hybrid approach can produce more accurate head poses. Next, I will introduce our stage 2. Recall that the second challenge is that there exists a significant ambiguity in the mapping from egocentric video to full body poses. Thus, in stage 2, we train a conditional diffusion model to address the one-to-many mapping problem. So our denoising network at each noisy level is based on a transformer architecture, as shown on the left. Here are the results of our full body motion given ground truth head pose as input. We can synthesize highly dynamic motions like kicking and jumping. Here are some comparisons with previous work. So now we have a complete 2-stage pipeline that can generate a full body human motion given an egocentric video. The next question is, how do we evaluate it? So to evaluate our full methods, we still need a dataset with paired egocentric video and full body poses. We can evaluate the pipeline on existing datasets, but they have limited scale and diversity. So to benchmark different methods on data with more diverse scenes and motions, we propose an automatic data generation pipeline. We leverage human motion datasets, AMAS, and 3D scene dataset, replica, and we put humans on the scene and detect penetration to produce the paired motion data and 3D scene data. Then we use AI habitat platform to render corresponding egocentric views given the head pose of the human motion sequence. And finally, we can get a dataset with paired egocentric video and full body human motion. Here we show an example of our dataset. On the left, we show an egocentric video, and on the right, we show the ground truth human motion. Next, I will show some comparisons that we estimate full body human motion from egocentric video. So given an egocentric video like this, we can generate highly dynamic human motions. And here's one more comparison. As shown here, our model can generate more realistic human motions compared to the baseline. Also, we show that with the same egocentric video, our method can produce multiple plausible human motions. And we show some results on the real-world datasets, GIMO. To summarize, in this paper, we address the problem of full-body human motion estimation from egocentric video. Our major contributions include an intermediate representation head pose to address the data scalability issue, and a hybrid approach to estimate head pose from egocentric video, and an effective conditional diffusion model to generate a full body pose from head pose. In addition, we contribute a large-scale dataset and an automatic data collection pipeline for paired egocentric video and full body motion in diverse scenes. So EgoEgo estimates human motion from egocentric videos, but it cannot handle interactions with objects. In daily life, humans constantly interact with datasets. So in our next project, we study the problem of human motion generation involving dynamic interactions. Our goal is to estimate full-body human motion from object motion, where the object motion can be easily obtained from the object's egocentric observations in the real applications. Specifically, given a sequence of object states as input, we synthesize the full-body human motions interacting with a given object. Since there are no existing datasets with high-quality object motion and human motion, we first collected a large-scale dataset with human motion and object motion to study this problem. Our dataset includes 10 hours of human-object interaction motions, featuring 17 subjects interacting with 15 objects. And I will briefly introduce our data collection process. We first select 15 objects and capture the 3D object geometry. Most objects are captured by filming a video and processing the video with advanced 3D reconstruction algorithms such as Luma AI. Then we conducted manual processing to clean the mesh for each object. We use motion capture to capture object motion and human motion at the same time. For objects, we attached file markers to each object to capture the object motion. And in each motion capture session, we use language descriptions such as pull the chair to move to guide volunteers to perform different tasks to ensure that the captured interaction is always meaningful. Here we show more examples of our dataset. So in this video, a human is moving a vacuum. Now we have this dataset with high-quality human motion and object motion. How do we address a task that synthesizes full-body motion from object motion? So there are two major challenges. First, different human motion can produce the same object motion. As shown in the figure, for the same object motion, there can be some variations in the human motion sequences. The second challenge is that to generate realistic interactions, hand-object contact constraints need to be enforced. Without the contact constraints, the generated result will have unrealistic interactions, as shown in this figure. So to address the first challenge, we use a diffusion model-based framework to learn the one-to-many mapping. However, naively learning a diffusion model to generate a full-body motion cannot ensure realistic hand-object contact. So we introduce hand positions as an intermediate representation in our framework. The reason that we use hand position is we can directly apply contact constraints to rectify the hand position, and then use the rectified hand position to predict full body poses. Specifically, we develop a two-stage approach. We first predict hand positions from object motion. Then in stage 2, we apply contact constraints to hand positions and generate full body poses from the rectified hand positions. So given a sequence of object geometry, we first encode object geometry representation as input conditions. Then we employ a conditional diffusion model to generate hand positions, including both left hand position and the right hand position. Specifically, we use a basis point set representation, which is proposed in previous work. At each frame, we project the BPS representation to a low-dimensional vector using an MLP and use it as input conditions for the diffusion model. At each denoising step, the diffusion model takes the conditions and noisy data as input, learning to denoise the input. And we use a transformer-based model as our denoising network. The training loss follows the standard DDPM formulation. We show a result in stage 1. Given a sequence of object states, stage 1 predicts both left and right hand positions. Then I will talk about the second stage that synthesizes full body poses from hand positions. Given the hand positions predicted from stage 1, we first process the hand joint positions using our contact constraints. Then we use hand positions as input to generate full body poses. So for the contact constraint, we detect the first contact frame by computing the distance between the hand joint and the object. Based on the assumption that once the object is in contact with the hand will maintain its relative position with a contact point on the object mesh. We compute the rectified hand joint position in the following frames. With the rectified hand positions, we use the same transformer model as the first stage to generate full body poses. We show a result in stage 2. Given the predicted hand joint positions from stage 1, our stage 2 model generates full body motions that are in correct contact with a given object. We show some results in the following slides. Here, the input is a table rotated to move, and the output is a human rotating the table. And here, the input is a moving vacuum. The output is a human moving a vacuum to clean the floor. We also developed a novel application that captures full body human motion by mounting a smartphone on an unseen object. As shown here, with visual inertia libraries like iPhone ARKit, we can capture camera motion using a smartphone. Then we can derive the object motion from the camera motion. And then the captured object motion can be used as input to our framework to synthesize full body motions. To summarize, in this work, we address the task of synthesizing full body human motion from object motion. We made 3 major contributions. So first, we proposed a two-stage approach, leveraging hand positions as intermediate representation to apply hand-object contact constraint. We collected a large-scale dataset with high-quality human motion and object motion. And we also developed a novel application that captures human motion with a smartphone mounted on an unseen object. So the previous 2 papers I just discussed estimate human motion from egocentric observations of either humans or objects. The next question is, how can we approach this from the opposite direction by generating egocentric observations from human motion? In our recent work, we propose a contextual interaction synthesis approach that can synthesize human-object interactions in 3D environments. So once we have the generate human motion in 3D scenes, we can easily render the corresponding egocentric videos. So why do we need to generate egocentric observations when we already have a motion synthesis model in 3D? So fundamentally, intelligent agents need to see the world through egocentric observations and understand human commands and interact with objects in contextual environments. Ideally, to train such agents effectively, we require datasets that contain paired human motion and corresponding egocentric views. However, as we discussed in our Ego project, obtaining such diverse and paired dataset is not practical. So we approached the problem from a different perspective. By training a single-aware interaction synthesis model first, we can then use this model to generate egocentric observations. And in this paper, we focus on the human-object interaction synthesis part. So given an initial state and 3D scene, language description, we generate a synchronized object and the human motion follows the text instructions. The problem is more challenging because first we need to know how to effectively leverage 3D scene and language information, and the other is how to ensure realistic interactions, including both realistic object motion and realistic hand-object contact. So to address the first challenge, we designed a pipeline consisting of a planning module and an interaction synthesis module, using sparse viewpoints as an intermediate representation. Specifically, given a language description such as lift a box, move and put down on the table, we use a large language model to automatically extract some key information, including interaction object name, target object name, and the corresponding primitive function name. We predefine a set of primitive functions, and each primitive function utilizes the 3D scene's point cloud with semantic labels as input to sample a point that meets our requirements. So in this case, we sample a point on a table, which will be the end object position. Then we use a habitat platform to plan a collision-free path from the start to the end. Okay, so the planning model provides sparse viewpoints. So we design an interaction synthesis model that takes the sparse viewpoints as condition to generate a complete human and object interactions. So directly employing a condition diffusion model, there are some issues. First, the object motion is not very realistic. It does not match the input viewpoint positions very well. Second, the human object contact is not realistic. For the first problem, we introduced object geometry loss to encourage the key point positions to match the ground truth key point during training. For the second problem, we leverage test time guidance during sampling. And we show that our trained model can generalize to some unseen objects. And I'm going to skip the comparisons. And also ablations. Okay, here we show the results of our whole pipeline. We first extract sparse viewpoints from scene and text using a planning module. Then we use an interaction synthesis module to generate long-term human-object interactions. To summarize, in this work, we address the task of synthesizing synchronized human motion and object motion given the initial state, language description, and 3D scenes. Okay. So we have explored how to generate human motion from egocentric observations and also introduced a contextual interaction synthesis approach that can be used for the opposite direction. And we are very excited about the future of human motion synthesis with egocentric observations. And thanks for listening.
Yeah, so it's been exciting to see all these talks. It's basically, it makes my job easier now. I don't need to motivate the problem so much. So basically, like one question that I'm asking myself is like, you know, we've all been blown away by how AI can solve a lot of tasks and like how impressive these language models are. But if you compare of how like a language model, like how AI is learning versus how humans learn, it's very different. So humans learn to interact since we are kids, and we learn to interact with the 3D world, with objects, with other people, and we build these mental models of the world. Then we go to school and like we learn like these more abstract concepts like language, mathematics, and logic. And eventually, you know, we have this network of people, and all together we have like this distributed knowledge. And this is very powerful. But if you look at the knowledge of every individual, it's pretty limited. We have a limited bandwidth in terms of what we can memorize, what we can, like the amount of bits that we can produce per second. It's all rather limited when you look at the individual. If you look at AI, like it's very different. It's like centralized. It's absorbing all the knowledge that humans created in internet, books, encyclopedias, and whatnot. And I think right now it knows more than any human on this, more abstract tasks like language and logic. So the question is, like, for people like that work on, understanding humans and modeling human bodies and so on. So I would like to ask, like, how many of you are working on 3D human capture? Okay. So, a natural question is like, does AI really need a body? And I think, like, for language, for abstract and symbolic intelligence, and for logic tasks, I think that we don't need a body. But and these are the tasks where humans, we are not so great at, right? We've come a long way, but it's been like thanks to these collaborative networks that we have. And when we look at like other tasks like sensorimotor intelligence, perceiving the 3D world, being able to communicate and engage with humans, there definitely AI, I think, needs a human body. And to capture and to understand the 3D world, to build these mental models, I think like several speakers already argued that we need to capture humans from an egocentric perspective, because like this we can capture like, humans moving in large environments for a long time, and we can capture these natural interactions. And for this we need like this wearable sensor tracking, like with IMUs and so on. And today we've seen like a lot of interesting talks on like capturing with IMUs, but it hasn't been always like this in the computer vision and computer graphics community. So this is a little bit like the storyline of my relationship with wearable tracking over the years. So actually, like my first paper in 2010 was on combining IMUs with cameras, and this was quite well received at CVPR. And then I published a further paper improving after that. However, I noticed that people were not really interested in these IMUs. They were like, it's intrusive, and like, we're more interested in this monocular 3D human pose estimation. And so myself, I also lost a little bit the interest. And but I was happy that then later in 2015, a student picked up my work, and then we started together working on egocentric tracking from IMUs alone, without cameras. This is Timo von Marquardt. And in 2017, we published this paper that is called Sparse Inertial Poser, which I thought for me was a breakthrough, because we were obtaining like a quality of tracking with only 5 IMUs that was better even than this prior work that I had, like where I was combining IMUs and images. And so here's like an example of these tracking results using only 5 IMUs. This was 2017. The camera is only shown for visualization purposes, but here we were just doing space-time optimization. So this sparked my interest again in tracking with IMUs. Then we had a follow-up work at 2018 where we had a deep learning version of this. IMUs were key to, if you work on human pose, you probably know the 3PW dataset. They were key to capture this dataset. So we have like also a fairly sophisticated optimization in order to capture humans in the wild. I also like worked partially in the self-pose project, where it's more related to what Christian was describing, like a camera looking to the person and estimating the pose. But today I want to like focus more on this capture of people interacting in the scenes. So in 2021, or well, earlier, actually much earlier, I had this vision of like, there's going to be at some point like a world model, like a world point cloud somewhere stored in the cloud. And, we could think of a problem where we're walking like through the world, and then basically we should be able to localize where we are in this 3D virtual world model. And this was the idea of this HPS work, which was also very well received at CVPR. So basically the idea here is that we will reconstruct the 3D world, and then we'll have a person like wearing a head camera and IMUs, and then basically we'll use like visual localization to know where the person is in the 3D scene, and we will use the IMUs in order to track the pose. So here on the left you can see the real image that is seen by the human, and on the right we see the synthetic rendering. This is the rendering of the 3D scene as seen from the human. And then we use the IMUs to track the person, and we also imposed physical constraints by the environment. I think there was a question related to this, so we actually imposed that the person should be always above the ground. And we then have a joint optimization in order to track the person. And we've seen now like follow-up works to this. This was the first time that we showed that we can track like a person like together with a large 3D environment. So here are some of the results that we were obtaining, and we were quite excited because it was the first time that we could capture these people right interacting in the real 3D world. And all the work before that, it was always tracking people in the void, and it's missing a lot of the interesting stuff that is happening because we move to act upon the world, right? We don't move in the void. So you can see here we're tracking 2 people, and the relationship between these 2 people is correctly estimated. Here you obviously notice that there is one thing missing. The object is not being tracked, so this is a limitation of this HPS work. We could track the persons, localize them in the 3D world, but we could not track the objects. So obviously, like we thought, okay, like that's the obvious next step, the obvious next thing that we should work on. We've seen like some interesting works that are actually dealing with this problem as well. So basically, the setup is the same. Oops, sorry. So here I'm showing the external view just for visualization purposes. And then we have like these IMUs, and we have the head-mounted camera. So the person is entering the room, and this is what you're seeing from the camera, right? And now the task is like when the person will interact with the object, we want to be able to like track the object. And the question is how to do this, because when a person is interacting with the object, basically sometimes like the person is looking away, or the object looks only, you only see partially the object, or it looks blurry, or there's too much like, clutter in the scene. So it's a really hard problem. So our take to this problem is like the human motion is telling us a lot of information about how objects move in the scene. So this is the key idea of this iReplica work. Can we infer object motion based on human motion alone? So this is the method. We're not going to use the head-mounted camera for anything else than localizing the person in the scene. And what we're going to do is we're going to train a detector that is going to detect when we have a contact with the object. And when there's a contact with the object, we're going to do interaction modeling, and we're going to drag the object along with the human for the duration of these contacts. So then the detector also is trained to detect the duration, so basically when the contact stops, and then at that point, like basically there's the interaction stops. And that's a fairly simple interaction modeling, but we showed that by using this simple technique, basically we can track a human interacting with the 3D world. Like for example, like here, the person will close the door, and basically we can detect when the person will get in contact with the door, and then we can drag the door along with the human. So here the human will interact with the table, and again, like we're tracking the table. So at the end, what we obtained with this work, which is iReplica, is a way of capturing humans interacting with the 3D world, and also capturing the 3D world dynamics along with it. So here are some examples. So the person is entering, now is interacting with this chair. So you can imagine that if you're in a metaverse setup where you cannot afford to put external cameras in every room in your house, then it's important to be able to track these changes in the scene from these wearable sensors alone. So this dataset is also available for research purposes. So we released the large-scale dataset of the 3D reconstructions and the motions and the IMU data as well. So I emphasize the only thing that we see, right, is the head-mounted camera view and the IMU data. Okay, so this is the capture part. We're also interested in synthesizing motion in scenes. So in this work, which I don't have time to describe, we basically showed how to synthesize human motion in scenes. And to generalize here, what we're saying is look, when you're executing actions you ignore most of the clutter in the scene, and at the end, like what you care about is avoiding obstacles and executing a goal action at the goal end. So here what we're showing is that by following a path and executing the goal action at the target location, you can generalize to many different scene geometries because you're actually ignoring the 3D scene. So it's in a way it's a bit like cheating, but it's kind of like making the point that sometimes you should not try to solve a very complicated problem taking every single thing that happens in the environment, because that's going to be hard to generalize. All right, so now let me switch gears. It's great that you give me the halfway through, because now we change a little bit the topic. So you've noticed that in this interaction sometimes there were some artifacts. It didn't look quite realistic, like the interaction with the objects, like the hands are not intersecting sometimes with the objects. So we need better world models. We need interaction models of humans and objects. So in this work, which is kind of a bit unconventional work, so typically people have worked on, given an object, what should the human motion be, right? It seems like the natural problem. But here we looked at the opposite. So we thought, okay, so if I know the human, can I know what the object pose should be, right? So this is what we call object pop-up. And this can be motivated by the Gestalt principle. So the Gestalt principle saying that you don't need all the cues in order to infer object shape. So for example, when I show you here A, B, C, D, I guess many of you in A can see a triangle, although there is no triangle. In B, actually, how many of you see an S? How many of you see a human? Okay, I can see a human, maybe because I work on humans. I can see this is the head and this is the arm. Anyways, the point is here you can see a sphere and here you can see the snake. The point is that we humans have these strong priors and we don't need all the information to complete the shapes that we're seeing. If I look at this video, I'm pretty sure many of you can imagine what these people are interacting with, right? This person is typing some keyboard, now is drinking from a cup of tea, now opening a banana, passing the banana to the human, now throwing it away, and now we'll step on the banana. So, and there is no banana, right? There's no cup of tea. So the question here that we asked is can we infer this object from human motion alone? Okay, so the answer is yes, you can, because there's a lot of correlations between humans and objects. And so what we do here is we encode the point cloud using a PointNet++ architecture, and then we predict the center of the object. Here we assume that we know the template. In follow-up work, we relax this constraint. But in this work, we assume that we know the template. And then we have, what is important now is we have to, this is just predicting the center, and then we just place the object in a canonical pose. And this might be wrong. And so now we have to fix this. And so what is important is to take into account the context of the human and the object. So we pass the human and the object to this PointNet++ architecture, and we predict offsets to the object such that the object now will align better with the human. So that's how it works, and we train this with a data set of human-object interaction. So in particular, we train on Behave and the Graph data set. So let me show you some results of this. So for example, this person is now holding binnacles, and the model just based on this point cloud can predict the object pose, as you can see. Here in red, we show the saliency points. These are the points that are most important to make this prediction. Now, to give you a concrete, more concrete application of this, you could imagine that you're in a VR setup, and you make a gesture of the object you want to interact with, and then a virtual object appears in your metaverse, right? To give some concrete application. So here there's a human, and then we can predict the chair the human is sitting on, right? So this is kind of the reverse problem. So another work I want to talk about is, which will be presented by Xianghui at this CVPR, is template-free reconstruction of human objects from images. So how many of you work on image-based human reconstruction or reconstruction from images? Okay, so the goal here is to reconstruct the human and the object from a single image. And this is an output that we obtain with our model. So I don't need to convince you that this is a hard problem. We have depth scale ambiguities, we have heavy occlusion, sometimes the object is not even seen, and if we think about interactions, we have diversity in humans and objects and pose and shape variations. To reason in 3D, we need priors of the interactions and the shapes. So as usual, if you work with 3D data, it's the lack of data. And we have data sets like Behave or Intercap, which have human-object interactions, but those are limited if we compare them to data sets of just humans or just objects. We have, like, for example, Bedlam or Objaverse, which are like of much larger scale. So now the question that arises is, like, can we combine somehow these data sets to multiplicate the amount of data that we can generate? And this is the key idea. We procedurally generate interaction data with diverse human object shapes. So we take interaction data sets like Behave, we take human data sets which are diverse in clothing and shapes and poses, and we take an object shape data set and we combine it with a Behave data set to, compositionally create a lot of data. So in particularly, we generate 1 million synthetic interactions of diverse humans and object shapes. So how do we do this? You need to solve different challenges here. So the key assumption is that we interact with objects of similar categories in a similar way. So if I take a chair, it doesn't matter like the type of chair, it will, like, the interaction will look pretty similar. So I can adjust the motion to adapt this to new chairs. So essentially, first you need to align, so contacts are going to be key here. We need to align the objects first, and for this we use an autoencoder that brings all the shapes into correspondence. And then once we have aligned the shapes, we basically can transfer the contacts from the source object to the target object. And now once we have the contacts transferred, then the problem is much easier. We can optimize the pose of the human such that it satisfies the contacts at the target object. And with this we can generate, for example, here you can see that we can vary the human and we can also vary the object, including the shape and the texture. So with this we can generate millions of data of people interacting with different object shapes and having different textures. And what is interesting of this work is that just training on this data, we can learn a model that can reconstruct from single images humans and objects, which I think it's quite exciting. Data is key, data is king, and we should pay attention to data, but you need also a good model, and here also we have contributions. So basically, our model is based on a diffusion on point clouds, and what we noticed is that if you predict the human and object jointly, it leads to an inaccurate overall point cloud. And I think it's because, like, the model spends a lot of resources, a lot of capacity in modeling both a human and object, and that's hard. So our key idea is to, well, another option would be, okay, then I'll predict like the human and the object separately. The problem is that then the model is not reasoning about interaction, and then the relationship of the human and the object is lost. So our idea is to learn in a hierarchical manner. First, we will predict like a coarse shape of the human and the object. So this model is based on, we had this before, right? We did. And this takes how long?
About 30 seconds.
30 seconds, okay, I can speak. Can you hear me at the end? Okay, good, yeah. So basically the model is based on diffusion on Gaussians. So basically on a Gaussian point cloud, you basically project each point to the image, extract features, and then this is denoised, such that this converges to the ground truth. So we first predict the human and the object together, and then we pass this through two specialized models which refine the human and the chair. And then basically you have the best of both worlds. You have accurate, detailed shape for the human and the object, and also you have the contacts. So let me show you a few examples. Here we can see like a reconstruction of the human and the object. And these are objects, and these are humans and shapes that have not been seen during training because we have only trained on the synthetic data, which I think is quite remarkable. And what I find really cool is that we had prior work where we had the assumption that we know the template, But now this new model works even better than our prior work, which was assuming that the template was known. So even without assuming a known template, we can beat the performance. So these are more examples of generalization onto COCO dataset. And again, we don't know the object, we don't know anything here about the images. Okay, to illustrate the advantage of reconstructing the human and the object separately as opposed to jointly, we use here a model like it's text-to-text, which can edit the texture of each point cloud separately. Okay, so far I haven't mentioned foundation models, and maybe some of you are thinking, oh, can you use foundation models to learn something about interactions? And I think we do. We have this work, which I don't have time to talk about, but I gave a talk yesterday, and it's available online, I think, in the Virtual Try-On workshop. The basic idea is that we have a 3D reconstruction model and a 2D multi-view diffusion model that are trained in tandem. So that at every noising step, we have a 3D reconstruction, we project, we have a render and compare and backpropagate, and we learn the two models at the same time. And what is cool about this is that I find this conceptually very interesting, because we're poking the foundation model to extract 3D information, and we use the classical 3D reconstruction methods to make the model actually 3D consistent. And so these are some results that we obtained. This is single image reconstruction. And what is interesting is that we never trained this model to generalize to humans and objects, but the model seems to be able to reconstruct objects reasonably well along with the humans, which I think is quite nice. We also didn't train for 2 people, but the model produces pretty reasonable reconstructions. So this is this is very new work. We put this on archive last week. This is almost the last thing I will talk about. I wasn't talking about this, but after Yuting's talk on, they were presenting a new model, and this is inevitable. There will be, simple, there will be key points, and some other people will come up with another representation. This is a problem that we have to live with this. But now we have a solution. So instead of choosing one model, you can now have, for pose estimation, we trained a model where at test time and at training time, you can choose what the model should predict. And for this, we use a canonical human, and then the user can select which points the model should predict, and then the model predicts in 3D these points. So you can predict the simple model, or you can predict internal key points. You can choose, right? So this is basically solving this problem of different kinematic models, different skeletons. This is called neural localizer fields. It's still not publicly available, but we'll put an archive this week. So I'm super, super excited about this work, because we also obtain state-of-the-art results. We can absorb all the data sets that are in many different formats using a very nice, elegant formulation. So all the data sets are available in our website. So just very quickly over the CVPR papers that we'll present, we had this neural pose NDF at ECCV, and we realized that we could do things much better, and now we have a much better pose model. So if you're using vPoser, reconsider and try our model, because it can produce much more variation for probabilistic inverse kinematics and whatnot. So I recommend you have a look at this, the code is online. We have also worked to texturize meshes using physically based rendering as well. So basically using text as prompt, we can basically texturize meshes. And the nice thing is that you can change the material properties here, because we have a PBR rendering in the process. And perhaps more related to this workshop, we also have work that, given the wrist motion, we can predict the hand motion interacting with the object. So the input to the model is the wrist motion, and it can produce the hand. I don't have time to go in more detail. Please talk to the PhD student. We'll be happy to discuss ideas. I think if you're working with virtual humans, you might be interested in this lecture. I put a lecture together with my students on virtual humans that covers all the materials since the construction of the simple model to clothing models and interaction models that might be useful. This was a lot of work, but I think people are using it. I'm happy that we did this. Okay, now very quickly the conclusions. So sensory-motor intelligence is one of the grand next challenges of AI. I'm really happy that more and more people are working on this, and we will see much more egocentric algorithms in the future, I hope. And egocentric capture and synthesis requires world models because there's so many ambiguities. You've seen this in all the talks so far. The world is very complex to model. Try to simplify things when possible, for example, like with procedural synthetic data generation or ignoring things in the scene that are not relevant for the task. And I think synthetic data generation and foundation models are a promising direction to incorporate these priors. And I would like to thank my team of postdocs and students who are really the ones doing all the work and the heroes here. It's really a pleasure to work with all these people. So all the datasets and software are available at our website. So if you want to take a picture of the QR code, we'll send you directly to the software. And now I'll be super happy to answer questions. Thanks.
I have one question. You talk a lot about the generation of synthetic data. How do you quantify the what is high quality enough, or what is enough quantity of data? How do you think about that?
Yeah, I mean, it's hard to do, but what we did is we look at the performance with different amount of data, and basically we have a progression that the accuracy goes up. It saturates at some point. Yeah. But it didn't maybe Chang-Hui can answer, did it really fully saturate, or we could push it a bit?
At least in our compute resources, it's kind of flattened a bit, but maybe with larger models, it can
go higher, yeah. So I think that's a very natural way of evaluating.
Join me in welcoming Manuel Kaufmann from ETH to present motion capture with egomagnetic body-worn sensors.
Thank you. Yeah, thank you very much. My name is Manuel. I'm very happy to be here. I'm a postdoc in the AIT lab at ETH Zürich that is led by Otmar Hilleges. And I'm also a tech lead in the ETH AI Center, where we are building a data capture platform for human-centric data. And yeah, it's my pleasure to talk about my work regarding electromagnetic body-worn sensors. We've just heard Gerard talking a lot about IMUs, and what I want to show here is actually why it's difficult to estimate body poses with IMUs, especially if we have very few of them. So what you're seeing here is the orientation that is measured by an IMU on the arm, and you can see that the pose changes drastically, but actually the orientation of the IMU doesn't change that much. In fact, it's quite easy to find two frames where two strikingly different poses could explain the same orientation measurement as we see here. And yeah, this is especially problematic if we consider only a few IMUs. And now there's different ways how we could disambiguate this. One is to use accelerations and lots of body priors, which is what recent work has done. That is really fantastic progress that we have seen, and by a lot of researchers that we see in this workshop today as well. And in my own research, I took a slightly different approach, and I investigated how we can use a different sensing paradigm to avoid this problem or to deal with this problem. And that is electromagnetic tracking, which is the topic of my talk today. So on the next few slides, I'm going to briefly talk about what electromagnetic sensing is, and the methods that we built to estimate SMPL pose and shape from these kinds of measurements. So in EM sensing, a source generates a fixed known electromagnetic field, here visualized for one dimension. And if we do this in all three dimensions, then a sensor can determine its position and orientation that is relative to the source by measuring the voltage that is induced by the electromagnetic field. And with this sensing principle, we avoid drift, which plagues the IMU-based pose estimation, and we natively measure positions. And then we can place such a source, which is a small cube, onto a person's lower back, and use about 6 to 12 wireless EM sensors for a full egocentric body motion capturing system. Now these sensors are wireless, and although EM tracking has been around for a long time, building this hardware in this form factor with also high enough accuracy is actually quite challenging. So I was fortunate enough that Meta took on this challenge, and even more fortunate enough that I could work with these sensors in my internship. And on the next few slides, I want to give you a little bit more insights in what we can do with these measurements and how we can estimate simple pose from 6 to 12 of such EM sensors. And to do so, we propose to use a framework called learned iterative fitting, which I'll explain now. So let's assume we are given a set of EM measurements, here abbreviated as X, and some initial estimate of the SMPL parameters, here abbreviated as omega. Then, in order to check how well the initial estimate fits the input observations, we can construct a cost function that we call LR here. And this cost function, what it does is it reconstructs virtual EM measurements given the current pose, and then it can compare these to the input measurements. And I'll explain again in a second how we reconstruct these EM measurements exactly. But it is clear that if we now minimize this cost function, we can then fit the SMPL model to these EM measurements to obtain the final pose estimate here. Now, instead of performing standard stochastic gradient descent to minimize this cost function, we use a framework called learned gradient descent, or LGD. And in LGD, we perform update steps that are very similar to normal gradient descent. So the usual formula you can see here. But instead of computing the gradient as usual, the gradients are actually supplied by a pre-trained neural network. And this allows us to bake strong human priors into the gradient descent step, which then results in a robust method that also converges fast. Typically, it needs about 2 iterations to give us the final result. And then the initial pose that we use for LGD is estimated by a simple recurrent neural network. Now, this architecture is a hybrid, so it performs optimization at test time, but uses a learned component, the network N here. To make this work, we need to take a closer look at the sensor measurements. So I'm going to zoom in here on the leg sensor as an example. So when we mount the sensors on the body, we do so rigidly with a strap. So we know that in theory the sensor measurement should move rigidly with the body. And applied to the SMPL mesh, this means that in theory the sensor measurement M here should coincide with some anatomical landmark, M tilde, on the SMPL mesh. But in practice, this is, however, not true in general. And there are several reasons for that. First, the sensor origin is not directly on the skin. And second, the sensor might also slip against the skin, especially during muscle contractions. And third, the EM sensor's accuracy actually is dependent on the distance from the source. So to address this, we model this difference between the landmark point on the SMPL mesh to the actual measurement with a simple rigid transformation, so a translational and rotational offset. And then we assume that by applying these skin to sensor offsets with a rigid transformation to the landmark, we approximate the actual measurement. So this means that we need to extract such skin to sensor offsets for every sensor and every participant. In the interest of time, I'm going to skip the details here, but suffice it to say that assuming we can get a simple estimate of the body from, for example, a multi-view volumetric capture system, then we can compute these sensor offsets and calibrate where the sensors are located on the body. So if you go back to our overview, we can now be a bit more precise and define that we use those skin to sensor offsets to go from the known anatomical landmarks of our given estimate to a reconstructed EM measurements by simply applying this rigid transformation. To train this architecture, we would need EM data paired with some poses, but unfortunately we don't have that. So what we are doing is we create synthetic data. We use the mass dataset to do so. And we use several of these skin-to-sensor offsets of all the participants that we captured in order to augment the data. And this gives us synthetic EM measurements with the corresponding SMPL ground truths. And this allows us to train this architecture. And then at inference time, we simply feed the real sensor measurements as input and use the skin-to-sensor offsets for that specific subject for the fitting. So there is no test time adaptation required here. Now with this hybrid optimization, we can estimate the SMPL pose and shape quite accurately. And in fact, the results were convincing enough that we thought we can use this system to capture reference data in the wild paired with RGB images. And that brings me to the last part of my talk here. So that's what we tried next with the EMDB work. Where you can see here a subject is wearing the sensors under their clothing, and we film the performance with an iPhone in addition to recording the sensor measurements, and we can record quite high accurate poses in the wild. So how do we achieve this? We use a method called the electromagnetic poser, or EMP, which is a multi-stage optimization procedure that works in 4 stages. In a first step, we calibrate the body by scanning a participant on a multi-view volumetric capture stage that we operate in our lab at ETH. And what we're doing on this stage is really just capturing a very short sequence where the participant is wearing the sensors, and this allows us to compute their SMPL body shape and also those skin-to-sensor offsets that we need for the fitting later. And then those quantities are fixed for the remaining stages. Then in the first stage, we fit SMPL to the EM measurements, very similar to what I just talked about before. So we minimize this reconstruction cost function, and this fit, as we know from the previous work, is quite accurate, but it is in local coordinates because all those EM measurements are relative to the source that we wear on the lower back. So then in a second stage, we need to figure out how the EM origin relates to our camera. And in this stage, we make use of self-localization feature of the iPhone and assume that the 60 pose of the smartphone is given. And then we define the tracking space of that camera to be our world space. To achieve then the alignment of the pose with image data like shown here, we perform another optimization in the second stage. And I will spare you the details, but what we minimize is a 2D key point reprojection loss, and we also keep some losses for 3D consistency. And you can see that we can achieve image alignment, but what's important to note here is that it's actually quite jittery because those 2D key points, we're using OpenPose here, are actually quite jittery as well. So then we add a third stage to clean this up, and we learn a neural implicit avatar model from this video sequence given the poses as input from the previous stage. And with this avatar fitting, we can formulate a dense pixel level loss that can help us to refine the poses. And as you can see here, after this stage, the image alignment works well and the poses are much less jittery and much smoother. So in fact, if we compare these two things next to each other, I hope I can convince you that this is actually very helpful. Now, because we track the handheld smartphone, we can also provide global body and camera trajectory, as we show here. And the estimation of global trajectories from single monocular video is in fact an emerging task that has recently garnered attention, and maybe you've seen several works that are attempting to solve this task, and we're happy to provide a dataset that can serve as an evaluation dataset. So with this method then, we recorded roughly 1 hour of data. As you can see here, some examples. That data is publicly available under the following link here. And yeah, as I said before, it can serve as an evaluation dataset for both camera local and global human pose estimation. And that is the end of my talk. Thanks for your attention.
Thank you, Manuel. Any questions from the audience?
Thanks a lot for the talk. I did not get the part how to calculate, how they get the global trajectory.
So that is essentially the AR kit from the iPhone.
Wouldn't this be subjected to drift because of the acceleration, the gyroscope?
Yes. So we don't exactly know how they do it. We did do some evaluations. And of course, there's a problem of drift. Also because they are not really doing any bundle adjustment. But we found that in the sequences that we captured, actually the estimation is quite good, and in the orders of centimeters for the sequences that we captured. But that is a limitation that we want to work on in future work.
Good afternoon. My name is Fang Zhou. I'm now a PhD student at Nanyang Technological University, supervised by Prof. Liu Ziwei. And now I'm really happy to be here and share our work on egocentric motion learning. This work was done during my internship at Meta with my wonderful colleagues. So as you can read from the title, in this work, we aim to perform egocentric motion tracking and understanding from multi-modalities using a language model. So language models nowadays are wonderful, especially their multimodal ability, as for example shown by GPT-4 are just mind-blowing. But I still not use it as an everyday AI assistant. Something's missing there. I think it's the context that is missing there. And you know, we as people moving around, interacting with the environment all day long. So out of all this rich context information, what we're really interested in is the egocentric motion. You know, there are multiple different data sources that we can gain from the egocentric capture system for that rich context. For example, we have sparse motion sensors, which can be found on wearable devices like smartwatches or smart glasses. They can provide basically poses of your body parts like head and wrists. And we can also use the egocentric videos captured by the smart glasses, like Ray-Ban smart glasses or the Aria glasses we use here. And there are already many wonderful works out there using these different modalities to perform egocentric motion learning. For example, egocentric motion tracking. There are like 3 points body tracking, 1 point body tracking. These are all topics covered today by those wonderful speakers. And also, egocentric video understanding is also very relevant here. But these works, they are not typically not focused on ego motion. So what we're really interested in is the egocentric motion. So we want to bring the motion in the language model. So luckily, there are a few works out there trying to do that in the past years. For example, the motion GPT, what they do is that they tokenize the motion and use a language model to establish the relationship between motion tokens and the language tokens. Come back to our framework. What we try to do here is that we want to perform motion tracking and motion understanding at the same time from this from multimodal data source. And as you can see that motion tracking and motion understanding are two very different tasks. One is pretty low level, requires accurate joint prediction. One is pretty high level, requires like natural language responses. So the key idea here is simple. We just treat motion as another form of language. And we use a language model to generate both motion and natural languages. And as it turns out, language models are very good at handling multimodal data, as shown by like vision language models like Lava. So this boils down to pretty standard 3-step training paradigm. In the first step, we train a motion VQVAE to tokenize the continuous representation of motion into discrete motion tokens. Then in the second step, we pre-train a language model using the motion tokens so that the language model can learn the distribution of motion. And lastly, we perform multimodal instruction tuning so that the model can learn to follow human instructions for different tasks. Motion VQ-VAE is pretty standard, but we still tried a few tricks to make it even better. For example, product quantization. Basically, we split the encoded feature into different parts and quantize them using different code books. So as you can see from our ablation studies here, without changing any other settings, with only one additional code book, we can get an instant boost in terms of the reconstruction performance. And now that we have a motion tokenizer, we can use the tokenized motions, flatten them into a sequence, and then use a language model to learn it using predict next token. Since we also want the language model to generate natural languages, so naturally we would use a pre-trained language model. But here's the problem. A pre-trained language model like GPT-2 we use comes with pre-trained text tokenizer and text codebooks. So how should we deal with the motion tokens? So it is pretty straightforward if you think of motion just as another natural language. We just simply expand the vocabulary or the codebook of this language model and train as usual. So pretty simple. And as a nice byproduct of this stage of training, we actually have an unconditional motion generator. So given a motion prompt, or the leading motion here, as shown by the red skeleton, we can randomly sample very diverse motion after that. So this also suggests that our language model can capture the distribution of human motions. And in the third step is the instruction tuning. So basically in this step, we want the model to follow human instructions to perform different tasks like tracking and understanding. So what we do is that we construct instruction, input, and output pair data and fine-tune the model. So for example, the instruction can be perform some tasks like motion tracking based on the given data modality like egocentric video and 3-point input. So the natural languages part are tokenized as usual as what you would do using a normal language model. And for the egocentric video, we use the clip embeddings here and project that through a linear layer and put it at this placeholder, clip placeholder. And then the same goes for the 3 points. Basically, we train a 3-point encoder to lift these 6 of poses to a high-dimensional vector. And then we concatenate these vectors together and throw them into the transformer layers. If we want to perform motion tracking, then the backbone would generate motion tokens, which can be decoded by the motion VQ-VAE decoder we had earlier. Or if we want to perform motion understanding, we can just have the model output natural languages. So for the experiment, we have 2 questions to answer. Firstly, does it even work? If you think about it, now that the language model is pretty busy, we have multiple different modalities, both at the input and output end. So it's a really challenging thing if you think about it. And the second thing is that is multi-modality really helpful because this kind of multi-modality setting was not explored before. So through our experiments, the answer to these 2 questions are yes and yes. So firstly, I'm going to show you visual results of our work. So as you can see at the top row, the left side is the input egocentric video. The middle is the ground truth skeleton, as well as our input 3 points. And the right side is our motion tracking results. You can see the upper body is pretty well constrained by the 3 points, but the lower body is not exactly the same, but also plausible. At the bottom, you can see our motion understanding output. So actually, by saying motion understanding, what we try to say is the motion narration. We want the language model to give step-by-step detailed description of the motion. Okay, so we also did a lot of quantitative evaluation. So for body tracking, either it's 3 points input or 1 point input, we can achieve comparable performance with previous works. So, but keep in mind that we achieved this by using a language model. So it's pretty interesting, I would say. And if we further add a second modality here, the egocentric video, we can see a fair amount of improvement in terms of the reconstruction error. So this is also pretty interesting observation because we treat this egocentric video using clip encoder. we extract the very high-level picture vectors and feed it into the backbone. So it means that it cannot be the model kind of cheat and spot which body part is in the frame. And also, you cannot always see your body parts from the egocentric video. So it must be that context inside the video somehow help the disambiguation of the human joint poses. So especially the lower part of the body, as you can see from this column. For motion understanding experiments, there are two key points here. Firstly, the multi-modality actually helpful. If you only use 3 points or the egocentric video as input, they are not as good as using both modalities as input. So this suggests that it's really meaningful to also use motion sensors for those egocentric video understanding, especially in terms of the egocentric motion. The second is that actually, if we use this multitasking training framework, meaning that we train motion understanding and motion tracking together, is better than if we only train motion understanding. So this is also the thing we want to see. And lastly, I want to discuss a few limitations and possible future directions. Firstly, the language model we use here is GPT-2. So in 2024, it's a pretty small model. So we want to, of course, experiment with larger language models like Lava. And I'm very excited to see how that works out. And secondly, the egocentric video encoding is not optimal in our work. As I said earlier, I encode each frame of the video into a one-dimensional vector. So we lose a lot of valuable information, especially spatial information here. So we can absolutely improve that. And also, since our framework is not specially designed for any modality, so we can just plug and play any other modalities. For example, we can replace 6-DoF poses with IMU. In case 6-DoF poses are not always available, we can also explore the usage of eye tracking. So yeah, that's about all I want to share today. Thank you so much.
Thanks a lot for the talk. I've recently followed the literature of motion understanding and motion pencils with the help of LLMs. And I always find that for the motion encoding, most of the papers use vector quantized PAE.
Yeah.
And I don't know why. Can you help me with that?
Yeah, thank you for the question. So I guess the biggest reason for me to use a motion VQVAE to encode the motion is that I also want to generate the motion. But if only for understanding, I guess there's no reason to, if you must use a vector quantized VAE, you can just use a linear layer to project that.
Do you think that using vector quantized VAE is makes a motion representation and subsequently generation limited because of the limitation of the core?
I don't think so, because like our motion VQVA is pretty well trained. The reconstructed error can be pretty low, and also these discrete tokens actually help the learning of the language model. Yeah.
Okay, thank you very much, Hanbyul.
Yeah, thank you.
So, hello everyone, I'm Siyu from Tsinghua University, and today I'm going to introduce our research on egocentric human motion capture with sparse inertial and visual sensors. And during this talk, I will also do this live capture of myself. And you can see that at the bottom right corner of the screen, I'm doing the capture. And this is achieved using 6 inertial sensors on my body. And so let's begin. First of all, I introduced the primary sensor we used. An inertial measurement unit is a sensor that measures acceleration and orientation relative to a global frame of reference. And these sensors are widely integrated into smart wearables such as watches, wristbands, phones, and even earbuds. And a commercial IMU module is as small as a coin. We can put these sensors on our bodies to capture the motion, just as easy as carrying a few coins on us. For motion capture, commercial solutions use 17 sensors for an accurate capture of the skeletal pose, while recent research has successfully reduced the number of sensors to less than 6, making it more practical and cost-effective for daily use. Our works majorly focus on motion capture with 6 sensors mounted on 2 forearms, 2 lower legs, and the head, and also the root. As we do not need vision or external base stations, we can capture the human in dark environments and also with occlusions. Also, we can track large range movements since our capture space is not constrained. You can see the second video, and we conduct a large range capture of the movement. And though appealing, this task is quite challenging to reconstruct full body motion from measurements on only 6 points of the body. For example, different poses like standing and sitting can produce identical IMU measurements. A similar example is raising my leg while keeping its orientation unchanged, like this. Okay, and this ambiguity makes the task challenging. So next, we introduce our works. The key to resolve the ambiguity is to learn the temporal motion prior. Our first work, Transpose, proposes to use 2 modules to estimate the human pose and translation separately in a sliding window manner. And in the pose estimation module, we first estimate the leaf joint positions from the inertial measurements as they are directly relevant to the input. Here you can see the real-time capture for intuitive understanding of our algorithm. And we just, first we estimate the leaf joint positions as shown here. And next, we estimate the full joint positions from the leaves. And you can see the capture. And finally, we solve an IK to get the human pose. And this multi-stage design greatly simplified the learning task. And in the translation module, we propose to estimate foot contact from the inertial measurements. We use a green ball to indicate contact and red for no contact. If a contact is detected, we can then fix the contact point to compute the human translation. And this works in most cases, such as the walking motion, where there is always foot touching the ground. And I can do this motion. And you can see that there is always a foot in green, indicating that it is touching the ground. And so when no foot contact is detected, we switch to estimating the translation by a network. An example is the jumping motion, where you can see that both feet are off the ground. And so in this situation, we need to use the network to estimate the translation. And this multi-branch design, again, simplify our learning task, thus enabling high accuracy. And if we say that the transpose is estimating the motion of the skeleton on the left, our second work, PIP, is to add bodies to the skeleton. And just now, we will consider the kinematics of the human skeleton, such as joint rotations and translations. Well, in this work, we further model the physics of a character, including the mass, shapes, and dynamics. And with the modeling of physics, we can not only capture more physically plausible motions, but also estimate ground reaction forces as shown by the red lines. Also, we can estimate joint torques rendered in red. I can render the ground reaction force here live. And for example, I can do some motions like this. And you can see that the forces are plausible and aligned with my motion. Yes. And in our method, we first follow transpose to estimate the kinematic states of a character. And from the joint rotations and velocities, we can compute the optimal joint angular and linear acceleration using 2 PD controllers. We then solve a set of forces to control a physical character to imitate the motion by producing the desired linear and angular acceleration. While on the other hand, with the estimated foot contact and collision check, we add constraints to the optimization to prevent sliding and penetration. The full method becomes clear. By combining the kinematics estimator and the physics optimizer, we successfully incorporate motion and physics prior. With this method, we can effectively solve the standing and sitting ambiguity by leveraging the dual priors. And in this lab example, the performer keeps sitting for half an hour, and our method faithfully tracks the motion all the time. I often say that pure inertial mocap is like a human walking with the eyes closed. Our next work, EgoLocate, opens the human eyes with a head-mounted camera. Pure inertial mocap is known to suffer from drifts, as there is no global positioning signals. While a camera simulating the human eyes, the drift can be solved. EgoLocate deeply combines mocap and SLAM, achieving simultaneous human motion capture, localization, and also sparse scene point reconstruction in real time. Our framework runs in two parallel threads, one for the human localization and the other for scene reconstruction, which we call mapping. Based on the real-time predicted motion from the PIP method, we refine the motion in the localization thread by visual odometry of the camera. Simultaneously, in the backend, the mapping thread continuously updates and optimizes the map by bundle adjustment. The full system outputs aligned human motion and map in real time. Here we show a comparison of our method with previous inertial mocap works. And the drift problem is obvious for previous works, while our method shown in white is the nearest to the ground truth shown in green. We also show live demos where the subject performs a series of much more complex motions, including the jumping and crawling and also fast rotations. The captured person successfully returned to the starting position after a 70-meter movement. Finally, we provide a preview of our new work, PNP, that will be presented at SIGGRAPH in August. We propose non-inertial effect modeling, addressing a shortcoming of previous approach. Due to the differential relationship between position and acceleration, we can utilize IMUs to estimate the joint positions. Well, the question is, does the differential relationship still hold true in a root relative manner? The answer is no. 4 additional terms appears, and we call them non-inertial effects, because they arise due to the use of non-inertial root frame. They need to be modeled during the post-estimation. And with this contribution, our method outperforms the state-of-the-art techniques in both research and industry. The left video shows a lab comparison with PIP, where the subject is simultaneously captured by the two methods in real time. And the right video shows a lab comparison with Sony Mokopi, which is a commercial product that estimates human motions from 6 IMUs. Finally, we make an outlook on future work. And we think motion capture with IMUs in sparse variables is a promising direction. And there are already some works targeting at this problem. Well, this is really challenging due to the reduced number of IMUs and the low-cost devices. And another future work is handling the magnetic interference. As IMUs are susceptible to bad magnetic fields, current works mostly assume a constant magnetic field. And while in real usage, magnetic interference is everywhere, and how to solve this problem is an interesting research direction. Before concluding, I would like to take a moment to acknowledge the tremendous effort and contributions of my co-authors. Their collaborations, insights, and also hard work has been invaluable to this project. We extend our deepest gratitude for their dedication and support. So that's all, and thank you for your listening. You can scan the QR code to find our work, and also welcome to our poster on tomorrow to see our work on motion capture with IMUs on the jacket. And I think I have about 1 minute left. so I can show some more live demos or compressed motions. And I will make this character larger. So maybe I can do some arm motions like this. And also I can do some leg motions. And also maybe full body motions. Jumping. And yes, so that's all. And do you have any questions?
Any questions for Siyu?
Yes.
Hi, I think it's a very nice work, so
thanks
for the presentation. So I have a following up question, especially that you combine the MPI stuff with the SLAM system. So in the video you claim that in the real you use real SLAM to help MPI to provide clip, but sometimes, for example, in the darkness environment, you will not use real SLAM.
Yes.
You will use real MPI to request the code.
Yes.
So how do you determine that when you will use real geometry or when you will use the MPI?
Oh, okay.
So that's
Okay, and in that system, we reproject the map points to the camera to refine the camera position. And when the camera did not, for example, it is black image and there is no key points in the image, and then that reprojection, in the optimization, we will not use the camera, the image cues to refine the motion. Do I answer your question?
Kind of. Yeah. So maybe I also have maybe another next question.
Okay.
So when you use the MPI and to request the pose, I'm wondering that if it's how do you exactly solve that if it's motion pattern is out of distribution? Do you think this is solved or is still unsolved?
Okay, as this is a data-driven method, so for some strange strange pose, SVO cannot handle this pose. But I think for most Eurogate scene pose and common pose, the system can handle as well.
Thank you. Okay, thank you, Xinyu. I just want to say thank you all for attending. This was the inaugural EgoMotion workshop. It was so exciting to see everybody come here and present their research. It seems like gradually and then suddenly is how EgoMotion and egocentric research can really take hold. So I'm really excited to see it happen here and be a part of it. I want to take an opportunity to say a huge thank you very much to Lingni Ma, who is really the primary force of this workshop. So thank you very much, Lingni. Round of applause. And all of the team and presenters who helped put this workshop together, including the team who are recording this so that more people can see it online. So thank you as well. All the best, and we hope to see you again next year. Thanks.